So, thank you, everyone. I'm delighted to welcome you all to our first workshop on Causal Neuro-symbolic AI. So, I, along with my co-organizers, Corey Hansen from Bosch, Yuni Susanti from Fujitsu, Japan, and my advisor who's joining online, Dr. Amit Sheth. He could not, unfortunately, be here because of his daughter's wedding this past weekend, but we are happy to welcome you here and want to get excited about this new and emerging field of causality and neurosymbolic AI. So giving you a brief overview of what is the goal of this workshop. So in this workshop, we have tried to come up with this is a field which we see upcoming, where it sees as a converging field of causal reasoning, neurosymbolic AI, and semantic technologies. We want to push the boundaries of machine learning systems, which are mostly correlation-based these days, towards explainability, more user-based causal explainability or human-like causal explainability or understanding. We want to bring together researchers from causal inference fields, symbolic reasoning, deep learning, and knowledge graphs to come together, discuss new ideas, and work on this exciting topics and projects. We want to discuss how causal and neurosymbolic methods can enhance our semantic technologies and explore new methods, challenges, and real-world applications of such. So why now? It's a good question, because we are in a world of generative AI where everybody assumes, at least out of academia, that LLMs or generative AIs can do everything in the world. They have achieved the AGI capability, which is artificial general intelligence. And some have read news clippings where they even mention that we might be on a road to ASI, which is artificial superintelligence. There's another new buzzword. I know many of us are not aware of this, but they're like, we're already on a path of AGI. We have achieved it. Now let's focus on ASI. So there's a growing need for structured, causal, and symbolic priors if you want these generative models to learn human-like understanding or at least be on a path of general intelligence. So exactly, that's where our workshop fits in. And it's a step towards building bridges between learning and reasoning from perception and explanation. So I would also like to thank our amazing program committee members. Some of them are in the audience right now, the authors who have submitted their papers, and the speakers who will be presenting, talking about their exciting work in our workshop. So let's dive into the world of causality and symbols, because the future of intelligence lies not just seeing the patterns, but trying to understand what these models tell us. So this will be our overall agenda. We have amazing keynote speakers with us. So we'll have our first keynote by Dr. Kersting. Then we'll have one paper presentation, short coffee break. We'll come back to our second keynote by Dr. Kun Zhang. And then we'll have our two paper presentations and then some concluding remarks. So it's my absolute pleasure to introduce our keynote speaker today, Dr. Kersting. He's joining us online. He's a leading voice in the field of neurosymbolic AI, probabilistic reasoning, and causality. He's the head of AI and machine learning lab at TU Darmstadt, where he's also a member of Center for Cognitive Science and founding co-director for Hessian AI, which is a Center for AI and Data Science. And his work bridges the gap between the symbolic reasoning and the statistical reasoning, exactly where our workshop lies in, at the same intersection. And he has made foundational contribution to statistical relation learning, lifted probabilistic inference, and more recently, neurosymbolic deep learning and causal representation learning. And many of his ideas have shaped how we think about embedded structures and reasoning into modern AI systems. He's also a fellow of European Association for AI and AAAI, and serves on the editorial board of several of top journals and conferences. And his research is not only theoretically rich, but also highly impactful in areas from robotics to healthcare. And please join me in welcoming Dr. Kersting as he shares his keynote on reasonable AI, bridging intuition and causal reasoning. Dr. Kersting, I think you can you can share your screen.
Yes, I hope you can see it.
Let me stop sharing.
Depending on which Zoom you are using, you may have to switch the display.
It's not coming up on my end, so I'm not even able to share my screen seat on. I think did you stop
Let
sharing?
me share again.
Yes,
Let's see.
Yes.
Do you see it now?
Yes, let me. Okay, so I'm going to move my Zoom to the second window. Okay. We are able to see it now.
Good. So thanks for the wonderful introduction. I think you're far too kind. And actually, you're the future, not me. But anyhow, I hope I can learn a lot here. I'm also super happy if we do not finish at all the slides. So interrupt me at any time. Just trying to tell you a bit about what I think is important in the near future, but also in the long future. And just, actually, I should have not shown it now, but because you did it already. But just to remind all of you, and all of us, I think it's completely wrong to always say AI equals algorithms for learning. There's such a rich class of problems we all tackle. Nevertheless, it is really exciting these times, because if even people like Terence Tao is arguing that soonish, even mathematics will not be the same as it was, and mathematical research will be done in a completely different way, we should start thinking at least about it. Likewise, last year we got 2 Nobel Prizes that are related to AI. You can argue whether they are AI Nobel Prizes or not, but they are, at least it's a strong indication that the saying it's always just a hype, I think that's also not true. And I guess at least AI stays. It has come to stay and will not go away again. And to be honest, use responsibly, but this is really important, responsibly. I really believe that AI has the potential to help tackling some of the most pressing challenges across multiple domains. It's not like it will do it magically on its own and being a big black box or black magic box and all will be done. But I think it can really support all of us in going ahead. And I don't think we have, in many questions, we don't have even a choice. So if I think of the German bureaucracy, and then also on the demographic change, then I don't see how we can handle it with a declining number of people who like to work on forms and getting things done in ministry. So I think there's simply no other choice, and we have to get together. So some people go even as far here, for example, Jeff Hinton, to say it's not just about AI, but what we are doing here and what we are witnessing is just that intelligence is a matter of scaling. So you just go for a larger model, you go for larger data and for larger compute, and then all of a sudden we see something smart happening. And you referred to that already. You may talk about AGI, you may talk about superhuman intelligence. There are many, many words for that. And to be honest, and to also apologize for it, we also contributed a bit there, because we were lucky also in getting our own little AI. Well, from an academic perspective, it's a supercomputer. From a corporate perspective, it's maybe a tiny computer. But anyhow, we got something like 35 million for building up our own superpod. And with that, we were able to do some contribution, some nice research, and also contribution to the model zoo, also together with people and friends from Stanford, from Toronto, and many other places around. And so, for example, I'm very happy that we can also make use of scaling laws in order to maybe do it in a smaller scale, reducing at least for learning, maybe not for inference, but for learning, then also the energy consumption. And then from the small networks, you can still argue somehow that if it performs well, scaling it up will also perform well. We also contributed, for example, to in text-to-image models, and you may have seen
diving into something super exciting and cutting edge in the world of image editing. Imagine being able to tweak a photo just by typing
so
out
you
what
can
you want
just
to
type
change.
in what you
Sounds
want
like
to have
something out of a
changed,
sci-fi movie, right?
and it is
Well,
changed.
it's real, and it's called Edits++.
You can add beards,
This amazing tool,
whatever you want to do. We also moved towards large-scale causality because actually it turns out that many of the explainable AI techniques, at least back then, they were not easy to scale to the large-scale models, because you have to either increase your memory, because, for example, relevance propagation, backpropagation, or relevance propagation, you may need extra memory in order to compute what is important in the input for the produced output. But then if you have already large-scale model, you don't want to do that because that's very costly. So what we did is we traded memory consumption by runtime, and we're applying an empirical approach, so several forward passes. And by that, you can then also approximate the input gradient, for example. And then you can also do that in a multimodal way so that you get, for example, this is a painting off. And then depending on how you complete or how an LLM is completing, you may get different heat maps showing you how that is anchored in the input modality of an image. Some people go even as far to not just say it's happening for machines, but what we're doing here is of importance to even understand our behavior. So, for example, one former editor of Wired, I think he might be in between with Science, I don't know. Anyhow, he's arguing that human behavior is so complicated that you cannot imagine to just come up with a single, maybe even gray box or even white box model to understand human behavior. So what we should do is, instead, we should collect data as much as possible, just have a bit of a deep neural network, and then we get the models that we need to make predictions. And because we have predictions, we as scientists, we can also try to understand human behavior. So in a sense, you may say it's not just about AI. AI is amazing, but it's bigger because it's really this GPT moment of human behavior, of understanding our own behavior by just collecting enough data. And there's several cases already now published in Science and Nature. Here's one of them, for example, Peterson et al. What they were doing, they were arguing that economic decisions can be done much better by collecting enough data plus a bit of a deep network, because then all the theories that may have developed already earlier are somehow covered in the data and then emerge by learning via a deep neural network. So I'm not sure how you feel about it, but it feels a bit weird because all what they are saying is collect data. They don't even care about interventions. They don't even care about hypotheses. They just care about data. And if you know a bit about science philosophy or philosophy of science, then at least they say throw away Karl Popper, because he argued that all observations and actions are hypothesis-driven. So we strongly believe that as well. And actually turned out that at least the science paper I was just referring to, they were having a strong data set bias, and they were simply testing in a slightly wrong way. So having a model is still beneficial, and it still pays off a lot. Now, even if you go for recent new AI models, maybe it pays off. Because I strongly believe, at least for now, and I also think not for the long run, maybe in the near future, but for now, scaling may not really result in reasonable things. So here, for example, if you are Sora, but you can also, you may have heard of all the talk by Rao's group from Arizona. You can also go really for planning, and they all do something wrong for now. And here you see blocks pop out of the blue. They got the right goal configuration, but they started with one block, ended with 3 blocks, many other issues that are happening there. So it is my strong belief, and that's why I'm super excited about your workshop, and that many of you feel the same, that the game is actually not over. And we have to build not just intuition, and intuition in quotes, because I don't think that we even know mathematically what is intuition, but somehow we are not just interested in correlation, not just in reflecting data, but we would like to build understanding. That means we want to maybe put our model ideas in there or get understandable models out of our maybe data-driven machines. So that's why we are pushing a lot what we call reasonable AI. Reasonable AI is this idea that you're not just having one monolithical deep learning approach, or even several subnetworks that you combine. But why not combining it with any other AI algorithm that we know, or even with a database or a database in an AI algorithm? And how does actually software engineering look like? Can we actually keep traditional software engineering? Why do we actually kill it? Why do we actually say that now programmers are not relevant anymore? And then we figure out later on that maybe there are many bugs introduced by large language models. So we want to have maybe a completely new view on what is computer science via the lenses of AI. So compositional AI, modularized AI, getting AI models working together in an easy way and in an open way, and actually serving us. So that's why we started to not talk about human in the loop, because it sounds like we are serving the machines, but the machine should actually serve us or be part of our society, but we are still ruling the society, so it should be rather AI in the loop. Now, that should be not really surprising to you, because at the core, we are just asking, can we realize with machines what Daniel Kahneman was proposing, having a system 1 and system 2, and be careful, system 1 and system 2 both can have symbols involved. So it's not just about symbolic versus sub-symbolic, but I guess it's much more about the reactive and the more deliberative system. That is, they are both maybe running even at different scale, but one is really reacting, one is really trying to understand, thinking about, reconsidering, going into actions. Just to illustrate that this is maybe really useful, you all know that we can have Atari games and other games now played by machines and also learned in a, well, what at least nature has said, self-taught AI. It's, in my opinion, not fully self-taught, because at least we were telling them what to learn and how to learn, and actually to learn it all, right? They don't have free will or decide to learn. But anyhow, it's amazing what these pixel-based systems can do. And here, for example, you see submarines. So the little yellow one is trying to kill sharks, collect divers, and by collecting divers and killing sharks, you can get points, and you would like to maximize your number of points. However, there's also the little white bar, which is about oxygen. And as you can see, though they get a lot of points, and here we are not using the very best agents, they quite often forget about the oxygen. And so they are dying because they are forgetting to breathe. So we were wondering whether we can provide this background knowledge that is actually covered in any manual for the game. And so what we were doing is we were not just using a pixel-based approach, but we were trying to use pixel-based plus object-centric. So we extract object information, and we combine both of them using large language models that are driven by a logical background theory. So if you put both together, then you can actually have two policies. One is then just following the pixel-based, and one is following the logical or the object-centric view. And you can now start to decide which policy to use, and you can use another LLM for that to decide, or any other mixture model you want to use to define on the input which policy to use. And then you can see early in the gameplay, it actually learns that oxygen is very important, and rather starts breathing than being myopic and taking more points. We are still not convinced. Here's another recent example. So if you look at image segmentation, then you can use, for example, SAM, the segment anything model from Meta. And then, for example, here you have this image with the boat and the people and their umbrellas. And then you can ask, for example, give me all the objects that are on the boat and that are holding an umbrella. And then because the boat is so dominating, apparently, at least within the SAM model, then SAM and variants of SAM don't get it, and they just give you back the boat. Now, if you combine SAM with a bit of logical information, you may even say causal knowledge, because if you think about holding an umbrella, it seems to be a causal relation. If we abstract for now how to model then that, the causal aspects, then you get actually back all the people on the boat that are holding an umbrella or that appear to hold an umbrella. And we do that again by combining different information. In particular, here we go on the completely symbolic part, but in a fully differentiable way. So we get from the visual input a scene graph. The scene graph generator is differentiable. Then we have the prompt. The prompt can be translated into a logical program. And then together with the differential forward reasoner and the segmentation model, we can get the right answer. And for that, we are using, and I will not go much into details, our languages that we have developed for dealing with logical reasoning in a more differentiable neural fashion. But you can use, I guess, many other languages, and people in the audience as well as from the organizers have contributed there as well. So somehow that looks very promising, but it's very tricky, because if you want to go the fully differentiable way, then learning darks, and darks are the first step towards causal models, doing so is quite challenging, and it depends very much on the settings that you have. So for example, if you use a log likelihood or RMSE setting, then actually, depending on the scale you're having in your data, you may get the wrong dark. You can counterattack that, as follow-up work was showing, by having a more flexible variance model. So we assume a fixed variance, and if you have a flexible variance, you can account for it, but then the learning becomes not easier. So what we were asking early then is, can we still get something like causal learning, but more in the neural way? And you can see where we are, what we are aiming at, because then maybe we can put that together like we did in the Atari games, and get a causal model together with a pure logical model together with a pixel-based model. Now here's an issue. At least mainstream standard DNNs, they are just, at its best, they are maybe something like conditional distributions. If you at all want to call them a conditional distribution, so you have maybe something like a softmax at your last layer, and all the rest is just input to this last layer, which is then deciding on a distribution. But they are definitely not a joint distribution. They cannot talk about the input, and that makes it hard to make use of them for neural modeling. Though yes, there are some work by Elias and Joshua trying to do something like that. But just to illustrate why that is tricky and making things harder, imagine that you take your favorite CNN, just a CNN, but you can also use a transformer, and you learn it on MNIST. Now you're not evaluating on MNIST, but you evaluate on any other data set, maybe with numbers or without numbers. Because you have no distribution over the inputs, it cannot understand that it's now looking at a different distribution at different inputs, and it will still tell you something like 0, 1, I don't know, whatever number, maybe not with a high, with a big difference in the output probability, but it still tells you something like a number. Or put it slightly different down here, if you try to get something like a likelihood, I mean, they are not providing a likelihood, but we try to approximate as much as we can do, you can see that they have the peak at the same position. So they are all equally likely for the model trained on MNIST. This model cannot distinguish the data sets. So can we do any better than that? Is there a computational graph approach for that? And if so, we can maybe use that then also to move up the causality ladder to get at other ways, or a more neural causal approach. So in one approach that has been pushed by Adnan and later on Pedro, and then many others, are probabilistic circuits. And let's see how to develop probabilistic circuits for those who have never seen them. So on the left-hand side, you see a standard truth table or probability density, right? It's a truth table where you weight all the different entries, so that the weights are between 0 and 1, and they add up to 1. And instead of working with a table here about x1 and x2, you can also turn that into functional representation. So you can go for 0.4 times indicator for whether x1 is true, times indicator whether x2 is true, plus 0.2 times indicator of x1 being true, times indicator that x2 is false. So here with a little bar, but you can use any other notation, and so on. So now you can also do simple probabilistic reasoning. So for example, if you want to know what is the probability that x1 and x2 are true, you put x1, the indicator, on true, the indicator for x1 being false, you put then on 0, right? Because x1 is not 0. Likewise, you do that with x2, and then what is happening is that only this upper part is 1, because you get 0.4 times 1 times 1 plus 0.2 times 0 times 0 times 1 times 0, and so on. So all the other entries, they're at least 1, 0. Now, you can not only get joint distribution, but you can also marginalize, and marginalization is happening if you put now the corresponding indicator function here of x2, because you don't care about x2, so x2 can be true, but it can be also false. You put both of these indicators you have for x2 to 1, and then you can see that you automatically start to sum the two different values where x1 is true. Right, that's fun. You get something that is computational, the marginalization, and you may start to control how much it takes, how much time it takes. So you may even have tractable probabilistic models, but that depends now on the functional form you're using. Now, to get closer to what people are used for neural networks, instead of a functional representation, you can turn that into a graphical or computation graph representation. So this is really identical to what we have seen before. And now you can start going deeper. You can go more shallow, whatever you want. So essentially, you can see that a joint distribution, well, maybe not all, depends on, can be encoded as a sum product computational graph, very much like what you know from neural networks. So you have simplified activation functions. That's all what you're doing here. If you now manage to get the computational graph polynomial in the size of the input, you actually guarantee to have tractable inference for probabilistic models. And that's pretty cool. I mean, you haven't really broken, I mean, you haven't proven that P equals P, but you can control now. And in Bayesian networks, it was much harder to control the inference in here. So we are somehow occupying a, in my opinion, sweet spot between what has been done earlier about either being more tractable or being more expressive. So going with Bayesian networks or tree-based Bayesian networks, neural networks that try to cover a bit of probabilistic distributions and so on. Now, if you relax a bit, what you have just seen, it's very simple. You can also say it's just a deep mixture model. And this deep mixture model, however, is quite powerful. And just want to illustrate before moving on to causality, why that is powerful, or that it is actually powerful. So here, for example, we were using these probabilistic circuits for Poisson distribution. So in the leaves, you have the Poisson distribution, and then you start mixing them together. So you make use of mixtures and independency assumptions. The Poisson is known, well, no one knows how a multivariate Poisson for more than 3 variables really look like. For 3, you can still do it by hand, but for our arbitrary numbers, and no one knows how the link function looks like and whether it is, well, you know how it looks like, but you don't know whether it will converge or not. So you may not be able to compute a multivariate Poisson distribution. So here we approximate by univariates, and univariates we know how to deal with. And so you can see that you can have positive correlation, negative correlation, no correlation, anti-correlation. And of course, in the leaves, you may even have some mixture model in a neural model setting. So recall, I was saying before, let me just remind you, that with a neural network, we have these issues that you may not distinguish the training set from any test set. Now, if you use one of these probabilistic circuits, then actually you can distinguish because you have a full joint distribution, right? And you can even ask what is the probability of X given Y, X of whatever. I mean, you can ask whatever you like, but you get a proper joint distribution. And then you can see that the peak for MNIST is really different. Keep in mind, this is log scale and this is log scale. And so the two different data sets really behave differently, which is to be expected because they look differently. You can also speed up by using what is called einsum operations that are featured by PyTorch, for example, so you can really scale well. What is most interesting for me is that you can now also start to talk about causality. Because if you think about it, at least the Judah Pearl way, what causality is all about, starting with a probabilistic model and then moving towards interventions and maybe even beyond at some point. So what you can do now is you can make use of a probabilistic circuit, let's say like you can see here in S1, but this can be over-parameterized. So imagine that you're now trying to capture, which you do anyhow by having a mixture, different distributions over X and Y, depending on. And now this can be used if you now take a neural network to control the parameters of your probabilistic circuit, depending on the interventions. So if you can get a neural network that is somehow modeling interventions by controlling the parameters that you're actually using, and by that knocking out even subnetworks or edges, if you assume that some Bayesian network might be underlying, then you can get something like a causal circuit, or we called it interventional circuits. So that is very much related to what Elias and Joshua and so on did in neural causal models, but now with a proper probabilistic underlying model. So not everything is just a neural network. And why is that interesting? I think we can now move to areas where we haven't been with causality. So imagine that you get a medical data where you talk about very different types of random variables, maybe random variables that at least I don't really know about what their parameterized distribution is. So age distribution, maybe one can even talk about extreme value distribution there. I don't know, but how is it really parameterized? Tricky. Lab tests. What should be the parameter? Is it? Can't imagine it's just multivariate. Maybe it is if we want to go for, is it just successful or not? But then maybe some of the lab tests are not just going for indicators, but also give you a quantity back. And then maybe you have to condition it on a continuous variable or on a discrete but infinite, countably infinite random variable. So it gets very, very tricky. But now we can abstract. And because we still do with univariate distribution going into this weird mixture plus independency into this probabilistic circuit mode, we can make use of what is called a characteristic function that's known from statistics as well. So imagine that you have a univariate distribution. Instead of dealing with the PDF, you're actually putting the PDF into the spectral domain. So imagine that you do a fast Fourier transform or a Fourier transform of your PDF. Then what you get in the spectral domain, it's called the characteristic function. And that is funny because essentially you're turning every discrete distribution even into continuous distribution, or let's say not distribution, but continuous space first. So moreover, if you have a characteristic function and you multiply it with a scalar, that's fine. If you combine them, so you have a convex combination of characteristic functions, then this is also a characteristic function. And if you go for a product, you're also having a characteristic function again. So essentially what you can do is what we did before with the probabilistic circuits, you can now also do in the spectral domain using characteristic functions. And you always get a characteristic function back, meaning you can back transform and you get some density back. Now that is very interesting because typically people have started, for example, to have a look at normalizing flows dedicated for discrete parts and then trying to make use of XOR kind of computations. Here, you're going a different way. You embed everything into the continuous space, and in the continuous space, you apply the same stuff. But you can do it, and you can get better estimates than previous mixed models. We have also tried, and others have contributed. But now, what does that actually mean? That means you can now combine the interventional circuit idea with the characteristic function idea and get what is called characteristic interventional circuits. So you can have now causal models in domains of mixed types of random variables, and you don't even have to decide on the inputs. You may have a discrete one controlling a continuous and a continuous controlling or influencing a discrete one. So I think this is very powerful and quite interesting, and let's see what we can do in the future in the medical domain, but also in climate change domains. So this is all going into, we develop new models, and I think that is super exciting, but there's also currently this trend of asking, do I have to go for new models? And I was happy to see that you were talking about that in the introduction, because somehow, as I said, intelligence is just a matter of scale, right? And you can go for what people call narrow intelligence to general intelligence and even to super intelligence. And some people feel like it's done. We are simply there. Let's collect more data, everything done. It's a bit strange, right? We saw already the failure modes before, but if that holds, then it may, at least that's my hypothesis, it should also hold for causality. Sorry for the typo in there. So can we argue now, why should I even bother to come up with new causal models? Why not just using any of the recent models? And they can also tell us what is causal, what is not causal, maybe even do the causal reasoning. So at least early we started trying to understand. And by the way, there's wonderful work in behavior science that parrots are actually quite smart. So when I talk about causal parrots, it doesn't mean that I feel like they are dumb models. I'm just saying they are maybe not on the same level as us humans for now. But we were able to show that they're pretty good in causality, but not perfect. And this may also be the reason might be that they are actually, if you look at their mechanisms, they are not causal at all. Indeed, there's something like causal attention, but that only means that you have a kind of temporal ordering in there. But there's nothing like an intervention. But they have been trained on all kind of human data. So in particular, they have been trained also on causal issues or causal domains, or they may have read a causal paper, right? So they have read a lot about causality and may then also talk about causality a lot. So that may also explain why, for example, you can use them in medical domains to get a good head start in modeling some of your issues. So we were looking, for example, at adverse pregnancy outcomes using a Bayesian network, so not fully causal already, but we just got the Bayesian network as an initial hypothesis and then used true clinical data to come up with a much better Bayesian network. So they might be very useful, but we should also not be surprised that they're not fully causal because there is no intervention. And actually, it turns out that these models behave much more like us humans, and we as humans are not really known for being causal. So there are very well-known studies in cognitive science showing that if you look at A, B, C, the chain condition, versus the B influences A and C condition, right? Knowing B, A and C are independent in both of these cases, so they're indistinguishable, but humans are known to prefer the ABC hypothesis over the B influences A and C condition. That's very well known. So what we did is we illustrated that this also holds for large language models because they are trying to mimic, because they get the very same kind of data, kind of human data only. So it's purely observational and purely just talking about causality, but not being causal type of data. And so you get very similar correlations. So you can say that large language models, as it looks like, have very much the same biases when it comes to causality than humans. So why is it then that we can still come up with maybe good hypotheses? What does it mean in terms of causality? So on the one hand, they are not causal. On the other hand, they can help us being causal. So first part in my last part of the talk was then to say, can we actually make use of them in a more co-pilot fashion? And yes, we can. There's also some other work. We went for something that we call the causal steward, and it's related to the causality, to the causal circuits or probabilistic circuits plus causality part that we did earlier. So essentially, you're putting now a large language model in a more they call it today agentic AI. So you have little agents, but AI per definition is full of agents. So let's say you have different subsystems, and the systems are starting to talk to you and trying to tell you, okay, with your data, we believe this is a good model. And then you may say, no, I think you should separate these two random variables. They are independent. And then you can keep going. And at some point you're saying, oh, I guess now we have separated enough. And then you can try to build up in a data-driven or expert-driven way your own model and then recombine these local models. So you have a kind of AI in the loop system by interacting with the human. So the expert can interact with the large language model. The large language model can decide to ask sub-problems being solved by other algorithms and getting, if you decide on the right causal partitioning, if you have reached it, it can then learn a data-driven way or by interacting with humans, getting back for the sub-problems, good hypothesis for a causal model, and then recombine to get an overall model. And it looks like combining data-driven, well, or at least let's say it looks like combining data-driven by trying to get them separated as much as possible. So the causal partition together with an expert together both into the loop is beneficial, because you can see that you can really get an increase in performance. Interestingly, using a REC system is less helpful than just using the AI in the loop. And that's what we are currently working on, because I think correlation and statistics is already not easy for most people, including me, and now putting causality in there, I don't think it will become any easier. So we need support by the machine, but the human should still be in control. But what is even maybe more interesting, and what does that all mean for causality? Because is it just trying out different causal models? Can we maybe come up with something new? We argued that they are not causal models, but maybe they are meta-causal models talking about causality. So what we are currently trying to understand better is the notion of meta-causality. What does it mean, maybe, that you have maybe even a logical system talking about a bunch of different causal models and selecting the one that is most interesting? But that's not only a discovery problem, but it's also an issue that you may observe in reality. So imagine that you have two agents, A and B. A might be the smaller one, might be the larger one, whatever. And then the agent A decides to just follow B. However, if you observe that happening, then your observed causation might be exactly the opposite, namely that B, whatever B is doing, A is following, right? So it's not that you can observe that A decided to follow B, so A is part of the reason, but it just looks like B is the cause or the reason for A following or for A's behavior, right? So slightly different. In a classical one, B is influencing A, but in the meta-causal, you can decide on whether that is the part or not. And in particular, you can model the decision of A to follow B. So what does it mean now? Intuitively, we say we have now also random variables that can influence the edges. So that is why we call it meta-causal. On a more formal way, but I'm not going into details, you can say that the environment is following a Markov process. You have an abstraction function with which you can try to abstract what is on a detailed level happening in the environment on a more abstract level to what you can understand. Now, on the more abstract level, you can start modeling SCMs, but you will get a bunch of SCMs. So SCM is structural causal model. So on the meta level, each of the SCMs becomes one state. So that is different, right? Beforehand, the random variables per se, the joint configuration were giving you states. Now you say the whole model becomes one state. And you can now say a meta-causal model is trying to connect these different SCMs. So you have a finite state machine, a transition function, depending on what you observe, to decide on which meta-causal states, which structural causal models are correct. And with this, you can do fancy stuff. You can do, for example, just understanding that if you want, for example, to model stress levels, so then stress can be attributed to the external, some external stress, but it can be also your own stress, that you start thinking about how you feel, and then you may push yourself into, oh my goodness, I'm not feeling good, so you get more stress and so on. So there are different states or areas you can act in. And you can express that now on the meta level, because on the meta level, you can say that all these structural causal models behave the same, but depending on what you decide, you're using a different structural causal model. So you're in a different structural meta-causal state. And that's exactly what we can show, at least on the modeling level. And now trying to understand how to do that, how to do structural learning in there becomes even more interesting. With this, I would like to conclude and rather start discussing. I hope there's a bit of a discussion with you, because I really think that your workshop is important, and that your workshop is about things that are that have to go together. So we have to get logic, but we also have to understand a bit of causality, whether it has to be a relational causal model. I'm not sure. They're getting even more tricky, but this could be one way. It could be that we use logic or some other programming language, even maybe hidden in a large language model, to control different parts or different models. So it could be a bit what they call agentic. But definitely we have to make AI more reasonable. So there has to be more reasoning in there, and the reasoning has to also be, at least to some extent, causal. And to give you just one very interesting problem in the near future that we should start working on, we have started, but I think there's enough to be done here, enough left to be done here, is that even your own causal model may change over time, but not as a temporal causal model, but more like you're using a model and you do a reflection about how you behave on a meta level, and then may decide on changing it. So you may have heard that judges become more critical, and the closer it becomes, they get to lunchtime. So the longer they had no food. And so maybe if you know that, you can adapt on the meta level your actual causal model you're using to make your judgments to behave in a more fair way. Talking about fairness, I think everything is fine, but we have to start thinking about what is the ideal world we want to live in? Is there a single ideal world? And who actually determines or decides on the rules? And to be honest, I think that is something where not just people like us, not just technical people, should talk about. We need input and discussions with sociology, psychology, with many other disciplines, and actually also with the governments, because that's something that is very critical, and I don't want to have that just as part of companies deciding. They are part of our societies as well, so they cannot decide on their own. But in any way, causality and combinations of neuro-symbolic, so neuro-symbolic and causal models will be the future to exactly tackle this issue. So thanks again for the invitation. Sorry that I cannot be around. Looking forward to our little discussion. Thank you.
Thank you, Dr. Kersting. That was a very exciting talk, and I really loved your take on AI in the loop rather than human in the loop. That's where we had been before the generative AI. But as we move forward now, we kind of put AI in the loop, or whatever task we are doing, we try to have an agent to help us with the task. And I'll open for audience to ask questions. I see we have anybody would like to go first, please.
First of all, thanks for the nice talk. From my first of all, can you hear me?
Yeah, I can hear you. I will try to repeat what you will have asked to see whether I fully understood.
Great. So from my experience, building ground truth data regarding causal relations and so on is quite difficult. So you often need a human or so to label this information. I mean, and you showed nicely that based on the scaling law, we can expect more in this direction. So I would be just interested in your take on this, if we still might have this scarcity in evaluation data in the future, or what we can do in this respect.
Yeah, so I fully agree. I don't believe that we will have a lot of data in the future, or most data we will have has been read already by some of the machines, and it's useless because of that. So that's why I think experts and humans are critical, contrary to what is discussed quite a lot in the news. Now, how to do that, I have no full understanding right now, but that's why we push a bit for the causal man, and also for what we called explanatory interactive learning. I haven't presented it here, but you can put explainable AI systems into the loop with the human. So you can ask, was that the right answer, yes or no? That goes back to work by Finale Doshi, and then we did something there. And I think we can replace now explainable AI by causal AI. But I don't think that we will ever come to a world where you will fully understand. I mean, that's also part of life, to not fully understand, but still to feel safe somehow, right? And I think that's a different story here. And again, this is something that is not just a technical question, but we need to understand sociology. We have to get cognitive science a lot in there to understand biases on the side of the humans and how they interact with the machine biases. So I think AI in the loop is the future together with data, because you may also make use of experimental design together with the machine to get better data. But we need definitely a more active AI in the sense of active learning. So I'm fully with you. I have no answer. We just have little baby steps into that direction, like here and also earlier. Which one was it? Where is it?
Yeah, thank you.
Yeah, final answer to your question. I think there has been no work on scaling laws for causal models, and that might be a super interesting but challenging problem as well. But I'm not aware of scaling laws for causal models.
Okay.
There are 2 questions online. Maybe I can, if you want to unmute yourself and ask, you're welcome to do that, or I can just read it out in the chat. Okay, so the first question that was asked was, how can I use causality in explaining medical image analysis?
Yeah, good question. Next question. No, it's a super interesting question. I think I would love to use something like our causal steward, or we can maybe also use, there's also a causal copilot-like system. But I would start from our explanatory interactive learning setting. So let me illustrate that. We got data, not in the medical domain, but about plants. So we got hyperspectral images of plants and how they react to biotic and also abiotic stress. And we use a CNN to predict whether a plant is healthy or not at any time. And we got almost 100% accuracy. And then the biologist, he was laughing at us. He said, you're better than the experts. That's very suspicious. So can you have a look? And we looked at heat maps or explanations. And actually it turns out that the system was looking at parts of the image that had nothing to do with the plant. So it was secondary conditions, if at all. So then we were saying to the system, don't use these regions. And so we force it to give reasons, at least kind of reasons grounded in the image, but they also on the plant itself. So now I think what we need, and we started with the causal steward on that, we have to combine that with causal models. However, as in the previous question already, it's not just that we need observational data or interventional data. I think at some point you need maybe then another subsystem that is not just trying to have a question answering session with you, but then saying, if you are right, then we should design an experiment that looks like that. And then some of us has to run the experiment. I can tell you that there are some groups working on, goes back to the old work by King et al. On the robot scientist. And now they try to put LLMs and agentic LLMs into a similar loop to run real wet lab experiments. And I think it will come. But we have to make sure that it's causal and that the AI is serving us and not the other way around. So I think we need a new part of the loop that is not done in the causal steward. We assume that the expert can give the answer, but there should be also an experimental design and experiment done or conducting experiment loop in there.
Thanks, Dr. Kersting. I hope it answered the question, I think, to the person who asked. Another question online is asked by Paul. He's saying, I'm curious about the way we talk about the AI or human in the loop. The human is mostly used to test and describe new directions. Is there any research being done on causal learning with an agent system that is able to imagine and execute experiments?
Well, it's related to what I just said. Maybe I confused both question already. So as said, I think there are some works. I know some people at the University of Osnabrück, followed by, I think, Tom Griffith people and so on. They've started to work on running actual experiments using AI systems. So the AI system is designing the experiment running the experiment, trying to get the results of the experiment, building a new hypothesis. These are the initial steps. As far as I know, they are not looking at causal models. So I guess we should combine with any of the causal co-pilots, causal stewards, whatever. But we should not have the illusion by just having AI agents, everything becomes easier. I think causality is hard for a good reason, because you want to understand, and understanding you have to sweat a lot for. But I think we will see it. We should make sure that causality and neuro-symbolic approaches have to say a lot there, because you want to verify that what you have done is correct and not just saying, I did some experiment. You have to be clear about what experiment you have done.
Okay. Just a clarification to check if I understood correctly. During the slides where you were showing the okay.
Yes, that will be.
So in the slides where there was the definition of meta-causal, if you go back to that.
Yeah, I will.
Which the relationship seems to be inducted by the policy that you define. I was wondering if that recall the fuzzy logic reasoning or the fuzzy logic paradigm, which that you might need the domain expert to come in and define the function that define the relationship between the implication between, or is completely something different that you are referring to.
No, well, I can't say no, I can't yes, just to repeat. So you are wondering whether it's a bit related to fuzzy logic and other even differentiable or weighted logic systems. Actually, I agree on you. For here, we were abstracting and we were calling it indicator function, so or identification function. So we assume that in your model, you know that in this case, you will go for that SCM, and if that holds, you go for that SCM model, but that can be uncertain as well. We haven't really explored that. We were happy to show that it's in principle doable, but it sounds very reasonable what you're saying. And I think this is where I believe we can make use of neuro-symbolic approaches quite a lot, where now the symbolic part is informing the neural part, not like in the neural causal, where the neural one was informing the causal part. And then, yeah, I'm with you. It sounds like a very cool direction. We haven't really explored. We haven't learned there. We have modeled on the meta level. Now, a bit like in Bayesian learning, you know, where you do learning by inference. At some point, it's unclear to me, is it inference, is it learning? It's maybe identical, but that's what we will see in the future.
Thank you.
Yeah, thanks for the talk. I like the slides you had. It said, you know, that scaling is not quite enough for intelligence. We also need causality. But scaling is quite important. And causal models seem to be quite bad at this. Or it's very computationally complex to scale a causal model.
Yeah.
I know that there's some work, and you mentioned the causal man work, which is, you know, somewhat looking into this, or at least how to evaluate large causal models. I'm just curious, what is the state of the art here, and how do we scale these causal models so that they can somewhat be able to reach intelligence, or to scale to the levels that the other neural models are reaching?
Okay, I think there are two, at least, no, I would argue there are three levels or three types of answers. So one is, which is biased, because I like probabilistic circuits, and probabilistic circuits are tractable. So I hope that scaling those will give you at least much larger causal model, or helping you to scale causal models to a larger domain. And we have a PGM paper on that, which is following the same argument there. Now, you also said, can we get to the same level as current large language models? I don't know. That's, I think, not just a question of the model, but it's also an engineering question, getting a large team. But there is another dimension to that, and maybe you don't want to scale intelligence just by causal models. So there is a line of research that's not part of machine learning, but that is saying if you have a fully causal model and you really capture the truth, then you may have to abstract in order to communicate to the next expert. And because you start to abstract, you're actually ending up with a correlation, to a large extent, correlation-based model. So there are some people that say large scale, in the sense of abstracted and communicated, you will never see a causal model, because then you would have to always communicate the whole world. But because you're not doing that, you abstract somewhere, and therefore you always have to stick to correlation. I don't know yet. I see a lot of value in that view as well. I don't know yet. My gut feeling is you don't want to have a fully causal model, but I want to not just have a correlation-based model as well. So maybe submodules where a correlation-based, if you're not trusting, can say, can you try to understand better? Maybe something like that, but I have really no clue. It's just the start of a journey. What do you think? What is your answer?
I have no idea. That's why I asked you.
Good. We should take it offline and start discussing a lot. I think, or you can do it at the workshop.
Yeah, we'll solve it here today. Don't worry.
Yeah.
I mean, there's work in neurocausal models using neural networks like no tiers and diffant.
Yeah, sure.
It's scaled to maybe hundreds of nodes. They claim maybe thousands.
Yeah, but this is far away from the billions and trillions in the large language models currently. That's why I'm saying I'm nervous whether you can scale to that size.
Okay, thank you.
Okay, in that case, I have one question for you, Dr. Kersting. So causality, as people have looked into recently, is talked about A causes B, B causes C types of connections. But causality is in a way much more than that. There are certain assumptions that we have to take into consideration. So there's causal sufficiency assumption, independence assumption, Markov assumptions. So I'm curious to know your opinion on how do we transform. So when we talk about neuro-symbolic AI and causality, so I believe we should also, in a way, look forward to incorporating the other assumptions and theorems which exist in causality into these into the neuro-symbolic AI domain. And I'm just curious to know your take on it, and everybody in the audience, if have any points to add to it.
Yeah, so I know, and I'm sorry, and I apologize for it that I don't know the authors, but there's what, at least, I mean, there's David Jensen's line of work, and then there's more recent work on relational causal models, where you just try to go from a relational logic and make it more causal. And the issue there is that the interventions are quite tricky then, right? Because depending on your intervention, you may have to break predicates and not only once, and refine predicates, and getting, in my opinion, quite messy, but it's maybe unavoidable for similar reasons as we just discussed. So one alternative could be that we are using neuro-symbolic, because it's also hard sometimes. I mean, you see the large language models are not perfect in logic, for sure not, but they perform pretty well already just on logical reasoning. So maybe there's an alternative of saying there's a language model and there's a causal model next to each other, and they talk to each other, they inform each other. So then the neuro-symbolic glue would be that a language and logical model is helping us to translate whatever is in the large language model into the dedicated concrete causal model. That's what we are currently looking at. It goes back a bit on work by James Cousins, where he used stochastic logic programs to describe families of Bayesian networks. And there you can have the theorems you were talking about on the meta level, in my opinion, but we haven't done it, but it looks like you can have them at the meta level so that they get respected automatically. That's what I guess. I don't know whether it was understandable, but I feel like we should embrace the black box, not formal knowledge in an LLM, and we should embrace the causal, very strict model, and maybe have them talking to each other instead of saying we have either the language model or the logic model. So that's what I believe in. And there, the neuro-symbolic is the glue around it, right? It gives us a formal language to talk about any causal model. So it's a bit like the language for the meta-causal logic that we try to aim at.
Thanks, Dr. Kersting. Okay, in that case, thank you so much, Dr. Kersting, for your talk, and it was an honor to have you here. The folks, our first
It was an honor for me. Thank you.
Thank you so much. I think we will move forward with our rest of the workshop. So we'll go with our first paper presentation by Uni Shasanti and Michael Faber on can LLMs leverage observational data. Can people online see the screen? So
I should mute yours, right?
So that
I think like this. Can the people online hear me?
I think so.
Yes, we can hear you.
Okay. Okay, so I will start my presentation. The title of our paper is Can LLMs leverage observational data toward fully data-driven causal discovery with large language models? And my name is Uni Shasanti. I'm from Fujitsu, Japan, and this is a joint work with Michael Faber from TU Dresden, Germany. He's also sitting on over there. Okay. Okay, so one of the fundamental tasks in various disciplines of science is to find the underlying causal relation and make use of them. So, for example, the causal relation would be like whether smoking causes lung cancer and whether taking an aspirin would cause an insomnia. So, this kind of causal relationship. And so that conventionally, the causal discovery estimate causal structure from observational data and generate the causal graph as a result. And this is using a statistical-based approach and called statistical-based causal discovery. So for example, suppose we have an observational data like this on the right side. And then with the statistical-based causal discovery, we will have the output on the left. This is called the causal graph. And then the causal discovery in the era of LLMs, there is this new concept called knowledge-based causal discovery. And basically what it means is LLM-based causal discovery. So instead of using an observational data, focus on the metadata, so more like the names of the variables or the textual description of those variables. And then, so rather than the actual data values of the observational data. And one of the other purposes of this knowledge-based causal discovery is to verify the causal graph from statistical-based method. So this is the causal graph from the statistical causal discovery method. And then for every pair, we ask the LLM whether the causal relationship is correct or not, basically this knowledge-based causal discovery. So one of the limitations is then it will, this method will depend a lot on the quality of the metadata, the textual description of whether, and the specificity, so how we describe our variable and our metadata to the LLM itself. And the other thing is also we fully reliance on the internal knowledge of the LLMs, make it prone to inconsistency and the hallucination of the other LLMs issues. So but even so, the progress in LLM, its advances in reasoning, especially in the text-based inference. So one of the question is, so can LLMs actually directly process observational data for the purpose of this causal discovery? So to inferring the causal relationship between pair using the actual data value. So can it handle those actual data instead of only the metadata? And so one of the challenges is how to basically, because LLM is prompt-based, so how to prompt those observational data for an effective LLM processing. And we've said like observational data, so what is actually an observational data? The key points here is it is a data collected by simply observing existing conditions. So there is no control experiment or intervention manipulating any variables. And for example, in the study of whether smoking causes heart diseases, so an example of observational data would be like a medical record, patient health record, for example, the patient age, gender, their smoking status, whether they smoke or not, and also their condition of the heart disease, whether they have, what is the condition of their heart disease. And yeah, for the other study, like whether a higher education spending causing lower employment, one of the example of observational data could be the data set from the World Bank, like the GDP of certain country, the employment rate, and those kind of example of observational data. So in the related works for this knowledge LLM-based causal discovery, there are several combination, and this is I summarize a bit. So one method is basically just direct prompting of the metadata. So just basically asking LLM whether there is a causal relationship between two variables with this and which one causing which one, something like that. The other is combining the prompt base together with a full with a supervised approach. And like on this here, the related works on the second, it's combining the prompting and supervised approach, prompt-based learning. And then the last is also some studies combined with the statistical-based causal discovery. In this case, the LLM is often used to extract the prior knowledge or like prior knowledge that will be used for the statistical-based causal discovery, or using the LLM as a feedback agent, those kind of combination. So this is the related works. However, as far as to our knowledge, there are no research yet that directly uses the observational data and ask LLM to basically somehow infer causal relationship from those data. There is one quite similar work here, but instead of using the actual data values, this work on the number 5 there, it calculates the statistic like a correlation between the variables in the observational data and give those statistics to LLM. So those are exist. So here we formulate the task formulation given a set of variables in the causal graph. So the objective is to infer the causal graph between all of this variable. And here the task is formulated as a classification task. Basically, we ask each pair of variable must be classified into those 3. First is whether the first variable causing the second variable, or whether the second variable causing the first variable, and last is there is no causal relationship. So yeah. So here our approach extend the existing KBCD knowledge-based causal discovery by integrating observational data directly into the prompt. So yeah, like for example, our so we need to prompt this observational data and immediately ask the LLM through the prompting. However, the observational data usually is quite large, and because of the limitation of the length of the prompt length, we apply some sampling function to extract some representative subset of the observational data to fit into the prompt. And we tried several common widely used sampling function here with a case size, the data, how much data we want to include in the prompt. And then this is about our real prompt structure. So the causal discovery is conducted using LLM by formulating structured prompts. Here our prompts will contain the V here is the variables. So basically the variables. K is any prior knowledge or basically any additional information that can help the LLM in a way. And the last is the observational data. And for the prompting strategy, there are a lot of new prompting strategy. Here we compare this quite common one, and that's quite recent. The first is the pairwise prompting, and the second is the BFS breadth first search prompting that is inspired by the BFS graph traversal method. We will explain for each prompting one by one. The first is pairwise prompting with observational data. So here, basically, we ask the LLM about the causal relationship between individual variable pairs. So given a variable pair, the LLM is instructed to determine whether causal relationship exists considering the given observational data. So here we are into basically the existence. So whether one variable is causing the other variable, and second is also if a causal relationship does exist, is it the first causing the second or second causing the first? And this is the real example of our prompt that we use here. You can see on the task part is the instruction basically to the LLM. Oh, sorry. And here the blue, here is the observational data. Of course, this is only an example, but yeah, as many, yep. And then here we give LLM the choices. The LLM should answer choosing the choices, whether, yeah, the first variable causing the other, or just basically one of the three classes category that LLM should answer. And then the second prompting method is BFS prompting with observation here. So the one of the merit of pairwise prompting is because you have to make all of the combination of all of the pairs. So it could be impractical when you have very large graph. So this BFS is inspired by the breadth versus traverse graph traversal. And so you will have less combination using this method. And so this is the real example of the prompt that we use in this prompting strategy. It's composed of several steps. The first one is called initialization step. Here you first identify all of the variables that are not causally influenced by the other variables in the graph. And then the second and also the third is the expansion. Here you identify the set of variables that causally influence by the current nodes, and you do it iteratively while inserting to the final causal graph. There is some certain strict condition. For example, if it is a loop, so you don't include that in the final causal graph, this kind of, yeah. So yeah, this is the blue part is where we include our observational data, and then different to the pairwise, here we don't give the option, and because we need the variables here. So we ask the LLM to directly respond with the name of the variables. We constrain the LLM output into, the name of the variables. So this is our experiment setting. We use this version of GPT for checkpoint. We conducted the experiment using the LLM for all of the experiment 4 times with a variation of the changing the temperature, and then we average the scores basically. And yeah, for the sampling strategy, we use the widely used sampling strategy. And for the number of the observational data included, for LLM based, because we have the limitation in the prompt length, we only include 100 observational data this time. And for the statistical based causal discovery, we experiment with 3 size. The first is using 100, and then medium like 500, and then 1,000 observational data for more fair comparison. We use these 3 benchmark dataset from the Bayesian network following the previous works. Our data is 2 in the biomedical domain, and 1 is in the more the general, and this is like a survey on the social study. And this is our result. We use the metrics of the classification task, precision recall of measure, and also this Hamming distance and ratio following the previous works. And then, so here we will discuss the result based on these 3 research questions. First is the impact of including the observational data, whether it improves the accuracy of the causal inference. And second is how does it compare to the conventional statistical based causal discovery. And then the last is we experiment with 2 prompting strategy, and now which one is actually perform better in our data in our case. So the first finding is, so incorporating the observational data does improve the performance, and it consistent across the both prompting strategy. So here, so you can see that it consistently improve. And on the pink part, the best performing model overall is also using the observational data, especially this BFS prompting. And And then the second finding is LLM-based method is improving over the statistical causal discovery method, and we get the consistent F-score improvement ranging from across all data sets. However, we also found out that the performance of the statistical-based causal discovery depends on the sample size. So as we can see here, when we use more data in the statistical-based causal discovery, we have less improvement, which just makes sense because more data normally. So to say that the LLM-based method will be more useful if, for example, you only have like limited number of data that you can use. So in that case, the LLM could be more effective. And then our third finding is that the BFS prompting method consistently outperform the pairwise prompting. And here, as we can see here, the pink part is the highest across all of the data set, basically the highest performance, and it is using this BFS prompting method with observational data. And we also observed the highest up to 0.32 points difference. However, in the BFS prompting method, it also included the entire chart history, which could lead to excessive prompt length. So that's also one thing to think about. So as for the conclusion, we investigate the potential of LLM for causal reasoning over observational data, and at least in our data set, in our current experiment, it outperformed the statistical causal discovery baseline, and also the improve over the LLM without observational data. So and our work demonstrate the potential of this combination of neuro-symbolic in causal discovery, especially using this causal graph structure plus neural method, which is LLM. And then as for the future works, we wanted to, especially the most important is how to handle this prompt length and how to choose the best, basically how to sample the observational data. In our current experiment, we don't find a lot of difference actually using several sampling methods, but maybe there are more advanced sampling methods that can give better improvement. So, thank you. That is our talk. So I would be happy if there's any question.
We go back to, first of all, thank you a lot for the talk. Very nice.
Okay, thank
Can
you.
we go back to slide 16?
16.
Okay. The results. So did you also compare your approach with other algorithms? Because you just use Pearson correlation.
Yeah, actually, for the statistical, we use only these two. Yep. And we actually take.
And the second question, but I think it would be interesting to look into more
recent
advanced.
Exactly. Yes.
Pearson correlation. And the other question was, you used 3 different data sets.
Yes.
And you used at the same time different sizes of observational data.
We wanted.
Did you also try it, like, for example, use the survey data set just with 100?
We did, but we did not include all of the results actually. Okay.
And how was that, for example, just out of interest? How would survey data set work with n equals 100?
So I think, for example, in this, when we use the survey using the 1,000, we observe like smaller improvement, but it doesn't happen to all the data actually. There are I forgot which one, Asia or Cancer, but there are also cases even when we use higher the more number of the sample, the difference does not really change, for example. So there is no, at least in our current experiment, there are no certain pattern. But at least in this certain example, we did observe that the more data we use, we get smaller improvement, but it does not happen to all of the data.
And what's your intuition of that?
I mean, naturally, because the statistical causal discovery depends on the data, so I would think that more data would lead to better result. But maybe, for example, in our certain data, it's quite common data like sorry.
I mean, one intuition, I guess, is the LLMs may just be confused, right? Getting too much data, get some kind of a cognitive overload.
That could be one of the reasons, to be honest. Yes.
Is that what you guess?
Most likely that also could be true. And also one of the other thing that I noticed, but I mean, need further examination, of course, is that rather than causal, maybe LLM actually just noticed the correlation on the data. But again, I did not do empirical research on that, but just my impression. Yeah, okay. I think you asked maybe first.
Yeah, so you said you would try the experiment with different temperatures and then average them.
Yep.
So I was curious, was there some performance difference between like temperatures?
Very slightly.
Okay, but not
Yep.
really.
Not really, not like very big, just slightly, yeah.
Okay, yeah. Thank you for that. I have maybe a stupid question, but did you try to test your models on random matrices of observational data?
So you mean like instead of using a real observational data, just random numbers? I mean, actually, I wanted to do that, but in the end, actually, I forgot. Sorry, yeah. But yeah, I mean, one of my colleagues, when I'm presenting this, he also suggested that, but I did not have time or I was forget. But yeah, you asked that. Now it reminds me of that, but for so far, not yet.
Yeah.
But I'm thinking of it.
Because if it doesn't change anything, it means that everything is related to the level of the variables. Or...
Yep.
Yep.
Could be only dependent on the metadata and does not look at the observational data at all, right? Well, that of course one possibility, but at least in one of our finding, we get an improvement when we add the observational data here. So but definitely it does have a meaning, but whether if we change this into completely random, it will also improve maybe, but that's I cannot say. But at least when adding it, it does improve compared to without any this data. Yeah.
That's a great question.
Yeah.
Like, what if you give like a wrong observation data?
Sorry?
What if you give a wrong observation rather than
Yeah, that is why, I mean.
Or you give a Pearson correlation matrix, but it's not the correct one.
Yeah,
You
that's
change the direction.
yeah.
Your positive and negative.
Yep, I should really do that.
It would be interesting to see.
Yeah. Sorry.
Sorry.
I don't remember the order of the question, so.
Okay, please, would you mind to go to slide number 3?
3.
Yeah.
Okay.
Here, I was wondering, on the middle of it, you established the causal graph.
Yeah, okay.
Could you please elaborate a little bit more? Why would I need to go in the knowledge graph?
Knowledge graph, sorry?
Yeah, because after causal graph,
okay,
there is the knowledge graph. Am I understanding correctly?
No, actually, there is no knowledge graph here. So on the
knowledge base, sorry.
Oh.
Knowledge base, so sorry, I made a mistake. Knowledge base.
Okay.
So why do I need to go in the knowledge base if I have already established
the causal graph?
Yes.
Yeah. So in this certain illustration is for this, basically the causal graph resulted from this statistical based causal discovery is we don't know whether it is correct or not, right? Because I mean, most of the time we don't have the ground truth. So what we want to show here is that the knowledge-based causal discovery could help in verifying those causal graph. So whether
why don't apply if I have to use the knowledge base, I go straight away and without building the causal graph, because that is your ground truth, if I understand correctly. So you are kind of verifying if the causal graph is complied with the knowledge base.
Actually, that's not what it really means in the certain illustration. We just want to show that the output of the statistical based causal discovery is a causal graph. Basically, what is whether there is a causality between certain variables in our observational data. However, normally this causal graph is verified by human expert, as far as I know. Yeah. And here, this knowledge-based causal discovery is trying to help or replace this human expert in checking whether the causal graph is actually correct or not. Yeah, so basically using LLM to verify this is just one use case of knowledge-based causal discovery, not exactly this research.
Yeah, just a compliment. So we are considering causal relation between two variables.
Yes, MOOC and
that's it basically. Yeah. We're not talking about more complex graph structures actually. So this is just an illustration.
Yeah, this is.
You could build up a causal graph based on several of such observations or such causal relationships.
Yeah.
If you want to make it more complicated, but it's actually not part of the study.
Yes, exactly. So this is basically just a little bit related works, what is called on this knowledge-based causal discovery. And one use case of this knowledge-based causal discovery is to verify the causal graph from the statistical-based method.
So is the motivation for what comes later then?
Kind of, yes. Sorry if it is confusing. It's not really related to the current.
The motivation.
Yeah.
Okay.
Yep, exactly. It's just to show what is happening in this causal discovery research in the era of LLMs. Yes.
Classical.
Yes.
Approach.
Yes.
Okay.
So it is called knowledge-based causal discovery, but this knowledge is not knowledge graph, but more to this LLM base.
Yeah.
That
So
uses knowledge.
The knowledge base is domain expert.
Exactly.
So after
exactly.
you get the causal, you put the domain expert to verify.
Normally, yes.
Yes, but you are.
But yeah,
Taking him off and put the LLM.
Exactly. The current trend is
now,
people
so,
start.
Thank you.
Yeah, people start to use LLM to replace the expert, kind of.
Yes. Okay. Thank you.
Yep. Okay.
Well, during the answer, basically the answer from the large language model.
I'm sorry.
Sorry, where all the answers
The
from
answers?
the answer from the large language model, taken with a truth degree of 1, or was also some kind of confidence value from log probabilities?
Oh, here we don't look at the probability. We just for example, in the pairwise prompting, we constrain the output to basically choose in one of the option, and at least I did not look at the probability of the LLM, the confidence of answering those. Yeah, but that could be interesting to look at whether LLM, how confident LLM in answering of each other. Yeah, we could look at the logit and that's additional analysis, I guess. Yep, thank you.
Okay. Thank you, everyone. And thank you, Uni. That was a great talk.
Thank you.
If you have any questions for her? So we'll head out for a coffee break now. We'll join back again in half an hour.
So we quit from the Zoom. I will just do it like this.
Nice to see you again.
So people online will you don't have to leave the meeting. We will join back again in half an hour. Let me just check the schedule. Yeah, thanks.
Is there?
There is one.
Can I steal some electricity from you? So is the door going to be closed?
No, the door is open. You can hang out here. It's like we're just going for a coffee break. We will be here. Yeah, we will. Yes, you can leave your phone here, and people online can join back again, or you can be online. We'll just stop the recording and join again at 4, maybe like 20 minutes. 20.
Uskata, is it better now?
Yes, a little bit.
Okay. Okay. So probably we have to go this way, just this way. Hello. Hello everyone. Thank you very much, Utkatani, for the organization of the workshop, the invitation, and a nice introduction. So today, as you can see from the title, I'm going to talk about the causal representation learning and generative AI. And by causal representation learning, I mean learning the underlying causal structure, including hidden causal variables and relations. And in the first part, you see the recent advances in causal representation learning. And in the second part of this talk, you are going to see the implication of causality in generative AI. So you can see how we can learn the hidden things and make generative AI more accurate in some way. Okay. So let's start with the story right here. As in Europe, I think you are familiar with this story. So, until the mid-19th century, puerperal fever was very popular, right? Because of that, a lot of women didn't survive after giving birth. So how could you find a reason? So basically, they found that in Vienna, there were 2 clinics with almost the same techniques, but very different mortality rates. And now comes the hero, Ignaz Semmelweis. Basically, he examined all possible factors by comparing the 2 clinics. And finally, he came up with the hypothesis that the puerperal fever was caused by some unknown, unseen, cadaverous material on human hands. Okay, and now you can see at that time he couldn't really see it. However, because of the comparison, he could come up with this hypothesis regarding the cause of the phenomenon or the disease. And then, just because of the hypothesis, he could just propose the intervention, which is very simple, right? Washing hands properly. And then the world became very different after that. So at that time, this hypothesis conflicted with the established scientific and medical options, medical opinions of the time. At that time, people believed that the disease was caused by the 4 humors in human body. However, later, this theory was accepted by the community because of Louis Pasteur and others. So now you can see, basically, whenever we could really discover the essential hidden entities or hidden laws, the world can become very different, right? And as you can see here, this is our world. So you can see what we can see is actually very limited, shaped by what we believe exists and how we understand it. From the observed data, we try to figure out the existence of hidden entities and their properties, and then try to come up with new ways to measure them or even manipulate them. This way, our world is becoming bigger and humans are becoming more resourceful. And however, this progress has been very slow. So to address this, our long-term goal is to develop an automated platform for scientific discovery. And this way, we can just take all the measured data as input and then produce plausible hypotheses regarding what should exist there, how to verify them, and so on. And this way, we can just keep increasing human world in a sustainable way. Okay, I'll skip this. So now let me just give some examples, motivating examples. Later we'll come back to these examples regarding how we can learn causality and how we can make use of causality to improve generative AI. So this is the first one. Right here, we have the data collected by our collaborator. So they measured 250 skeletons in the world and 8 variables of the 250 skeletons, and they try to see the causal relations among different features. So now you can see in this case, first of all, we cannot really do any intervention to see the consequence. We can only make use of the observed data and try to see the causal relations among those features, including geodistance, climate, diet, cranial shape differentiation, and so on. Okay, later you can see the result. Now comes the next problem. So each of us try to understand our personality, but how? We can never directly touch our personality, right? We even don't know how to really figure out where the personality should be. Instead, we can design questionnaires, and then from the answer scores, we try to infer the underlying mental conditions, right? So in this way, we can try to infer the underlying hidden causal variables and relations. Later, you can see how we can automatically determine the dimensions of personality by making use of the answer scores as a typical causal representation learning problem. Now let's look at generative AI. Specifically, let's look at a the result of image generator. So we have been doing these experiments for 2 years. So the prompt is a peacock eating ice cream. So this is a very unusual scenario. However, we can produce some sensible picture, right, from this prompt, because we know what you mean by peacock, what you mean by ice cream and eating and so on. So basically, we know concepts. We know relations among the concepts. Now comes the result by Stable Diffusion produced 1 year ago. You can see, yes, it's a very nice picture, but where's ice cream? And why? This is very simple, because in the training data, there is no such a picture, right? And it's very hard to generate something very plausible. And months ago, now you can see with DAR3, it's much better. However, if you have a closer look, you can see something similar. You can see something interesting. Right here, you can see in almost all cases, peacock is using human hands right here. And actually, it's not really eating, right? If the beak just touches the ice cream, it's not really eating. What's the problem? Now you can see they can try to put things together, but not in the right way. Later, you can see how we can solve this problem. Okay, now comes the first essential question. What's the difference between causality and dependence, right? We know causation implies correlation, but the correlation doesn't imply causation. But this way, I don't think this statement is fair. Maybe it's better to say correlation doesn't directly imply causation. However, in almost all cases, by analyzing observational data, we can really see something about the causality. So basically, this caricature explains my experience. When I was very young, I used to think correlation implies causation. And then I still remember I read a book at a rail station. And then I was so astonished because there were so many examples where correlation does not imply causation. However, after doing research in this field for quite some years, now we are very optimistic. Essentially, under some assumptions, in almost all cases, you can really infer information of underlying causality from observational data. So what's causality? We say two variables are associated if and only if they are dependent. It's very simple. And when we say X causal Y, we mean the effect of interventions. So we cannot define causality just at the statistical level. We have to go to another level. So we define intervention first, and then we can see the consequence of interventions. Intervention is defined this way. Intervention on X, say rain, is defined this way. We can only change this variable directly, but not any other variable, at least for the moment. What does that mean? It means that if I do intervention on rain, I could only directly change rain, but not anything else in the system. So this way, if I later, or at the same time, if I observe another change, I know this change must be the consequence of the variable I intervene on, right? So then this way we can say X causal Y if there exists different, this intervention on X to set X to different values corresponding to different distribution Y. Since this intervention changed only X directly, now we know, yes, the difference in Y distribution must be caused by the change in X, and hence X is the cause of Y. Of course, you may say this definition is circular. Why? Because if I have no idea about the causality, how can I make sure this is the intervention? Given that the intervention can only change the target variable, but not any other variable directly, right? And at the same time, if you can do intervention, you can define causality, or you can determine causality. However, a circular definition is still useful. Later, you can see by making some proper assumptions, we can just go to this circular world to make sure things are causal. Okay, so this is the outline of this talk. I will just briefly report the recent advances in causal representation learning. I will briefly mention 3 cases, including the case with ID data, independent and identically distributed data, and then I will talk about time series data, and then we can have a look at the scenario with multiple distributions. In some way, we can say this is a heterogeneous case. And then let's see how we can just make use of the text-image pairs to really understand the concepts, and then do precise generation and refinement for generative AI. So this is a very famous example. Right here, you can see the number of chocolate consumption per capita per year is clearly nicely correlated with the number of Nobel Prize winners, 10 million people, right? And if you take log transformation, you can see the relationship is almost linear and the correlation coefficient is very high, right? Statistically speaking, this is very nice because the correlation is very high, but from our perspective, this may mean nothing. Why? Because without the causal understanding, we don't know what to do. Essentially, we want to understand so many things for the purpose of making changes, right? So if you know that chocolate consumption is a cause, then we can try to say distribute the chocolate right every day. But later, actually, in my class, by collecting some other variables, we can infer that no, there are no causal inference in between. Instead, the two variables have latent common causes right here. Just from data, you can discover such information. Okay, now how can we solve the problem? We have to discover causality from observational data. So this problem was known as causal discovery traditionally, and recently in machine learning, people have been using causal representation learning. Essentially, they mean the same thing. However, for historical reasons, they may focus on different aspects of the task. So generally speaking, in causal discovery, we try to recover the underlying causal structure from data. And by definition, the causal structure should contain hidden causal variables and relations. However, some time ago, some people believed that we can only make use of the causal relations among the measured variables for the purpose of intervention, right? That's why they mainly focus on the causal relations among the measured variables. In contrast, in causal representation learning, very oftentimes we start with low-level raw data like pixel data, and try to infer high-level latent variables like concepts and relations and so on, right? But basically, both of them try to find the underlying causal representation. So you want to go from the observed variables to the causal representation so that you have a causal explanation, right? And very oftentimes we have latent variables. So the first question in this part is whether this is possible, right? Because a lot of people say, oh, you cannot go from observational data to the underlying causality. That's true in some way. However, with this example, you can see, generally speaking, we always make assumptions. And with assumptions, very oftentimes the problem can be naturally solved. This is a question in the homework assignment for a 4-year-old. Now you can see, basically we can determine the order of the events, right? So which one is the first, which one is the second, and so on. Now you can see, without any difficulty, a lot of people will say, oh, this one should be the first, this one should be the second, third, fourth, and fifth, right? This is the causal or temporal order. This is also causal order, right? So yes, the teacher will say, yes, genius, right? This is right. However, it's also possible to have different solution, different answer. For instance, I may say, oh, this is the first one right here, and this is the second one, third one, fourth one, fifth one. Why? I can say, so at the very beginning, you can see the kid was running. That's why the kid was sweating. And accidentally, the brush has the same color as the painting, and so on, right? You can see a lot of accidental patterns. And then later, the kid started removing the painting from the fence. And finally, after getting done, the kid also washed the brush and everything, right? So now you can see this is also a possibility, although the chance is very, very slim. Why? Because there are so many accidental patterns, right? So this violates the simplicity assumption. So basically, with some kind of simplicity assumption, we can recover temporal order and hence the causal order, right? So basically, this is the idea behind the causal discovery and the causal representation learning. Okay, so how can we solve the problem? Basically, all methods for causal discovery or causal representation learning rely on one property of the causal system. It's known as modularity property. What does that mean? All variables can be dependent. However, from a causal perspective, you can decompose the whole system into a set of separate processes or modules. Those modules do not share any information. They don't share parameters, they don't share anything. For instance, here, rain, wet ground, slippery are dependent. However, we know that the process to generate rain and the process to generate wet ground from rain and the process to generate slippery ground from wet ground are completely irrelevant to each other. They are independent modules in the world. They don't share parameters or anything. You can change one without changing any other. So from this property, modularity property or exogeneity property in economics, or independent causal mechanism formulated in machine learning, then you can derive statistical properties of the variables. For instance, given x, you see z and y should be conditionally independent. Why? Because when I try to determine y, as long as I know the value of x, I don't care about z. It's a different module, right? And this is the conditional independent relationship. And with this, we can develop constraint-based method for causal discovery. Furthermore, now you can see right here, when I consider the process from wet ground to slippery, I have noise. And if x and y, wet ground and slippery, do not share other latent common causes, then this noise term E should be independent from the wet ground. Why? Because E is generated from another module that don't share information. So this is known as independent noise condition. Okay? E and X should be independent as two causes of slippery. Later you can see with this condition, we can even find the causal asymmetry. And of course, if you have non-stationary environments, things can change. However, you can argue that for the right causal model, it enjoys minimal changes, which is to say that only a minimal number of modules should change, and at the same time, if they change at the same time, they change independently because they don't share information. Okay, so basically, all methods can be derived from this perspective. Of course, at the same time, we have to assume some kind of simplicity conditions so that we can find the right model. Now let's look at the setting of the problem. So basically, there are three axes of the problem of causal discovery or causal representation learning, including whether you have ID data or non-ID data, whether you can enjoy parametric constraints for the mechanism or it's parametric, and whether you allow a lot of latent variables. And right here, you can see a summary of the recent results in this field. So we will start with the ID data right here, and then we can consider non-I but ID data, which means we have temporal dependence. And finally, we are going to look at the situation with I but not non-ID data. So in this case, we have independently distributed data, but the distribution is not identical. In other words, we have multiple distributions. Then you can see in each of the cases what we can get. Okay. So roughly speaking, with ID data, the solution is usually pretty weak. Why? Because statistical inference and causal discovery are very different. In statistical inference, we like ID data. But causality basically aims to understand and apply changes. That's why whenever there's a change or temporal information, we can heavily benefit from such information in order to discover causality. So you see, in the latter two cases, usually the results are much stronger, even if the model is non-parametric. Okay, so now let's go. Remember this example. So Marlin Nobeck, with a great last name, Nobeck, collect the data right here with 250 skeleton and 8 variables. Here you can see the data. So this is ID data. We have single distribution. Here some variables can be high dimensional. For instance, the cranial shape differentiation is 255 dimensional. And we don't know whether relations are linear or nonlinear. Actually, many of them are nonlinear. So here we don't have parametric constraints. And you may have or you may not have latent variables, but we can do both. So in this case, you can see we don't make use of constraints on the mechanisms. However, we can still make use of conditional independent relations in the data. Here you can see a very quick picture of constraint-based method for causal discovery right here. So the typical method is called the PC algorithm. Peter Clark basically is Peter Clark and my senior colleagues at CMU. So right here, with the PC algorithm, if you assume there are no latent variable or latent compounder in the system, and if you have enough ID data, then it's guaranteed to converge to the truth. Although in many cases, the result may not be so informative. Similarly, even if you have latent variables, FCI is guaranteed to be asymptotically correct. However, because it makes use of only conditional independent relations, very oftentimes the result may not be very informative. Whenever it is possible to include a compounder, it will say so. So as a consequence, it could be you may want to make use of other constraints to further refine the result. Let's look at what I mean by that. So here, this is the procedure. We have data on the left, and then from data you can discover independence and conditional independent constraints. And then whenever you see, we start with a completed graph with the PC algorithm. So whenever you see independence or conditional independent, you can remove the link. Okay. So this is because under the condition of causal Markov condition and the faithfulness assumption, we know that two variables are conditionally independent given anything if and only if they are not directly causally related. So 1 and 5, no link. 2 and 4, no link. 2 and 5, no link. 4 and 5, no link. And 1, 3, no link right here. And then after this, you can try to determine causal direction. For instance, here, if you look at the relations among x2, x4, and x3, now you can see 2 and 4 are conditionally independent given 1, but not 3. Then this is the only way for them to be related. This is known as V structure, or we say this is an unshielded collider. We say x3 is an unshielded collider because it's a collider right here and it's unshielded. There are no such a thing. So in this case, we can determine V structure, and this is the only possibility. And after that, we can try to determine other direction by doing orientation propagation. So here, if you try to see the relationship between x3 and x5, now you can see that it must go this way. Why? Because if this guy goes this way, then we are going to have a fake V structure because x2 and x5 are causes of x3. Then x2 and x5 should be marginally independent in this case. But in the data, you can see they are independent given x3. So we can avoid fake V structures and so on. And finally, this is the result. Basically, you can see some links are directed and some links are not, right? And at the same time, in PC algorithm, we don't allow latent compounders. So later you can see how we can address those two issues, right? To allow latent compounders and to determine the orientation for all edges. Okay. Now comes the result on the archaeology data. So here we produce a platform called Causal Learn. So it's publicly available and with a lot of methods integrated. So we have the data set as the input, and on the right you can see the output. So geodistance is a cause of climate and the cause of cranial shape differentiation, cranial size, and so on. And also it's a cause of diet, and the diet is finally a cause of cranial shape differentiation. So basically what you eat can change your looks. However, relative to this set of variables, this causal influence from diet to cranial shape differentiation right here is not direct. It takes place via another two variables, including attrition in teeth and some other behavior. Now you can see with a causal picture, everything is transparent. For instance, I can still eat what I want to. As long as I can protect my teeth and try to avoid some behavior, then my cranial shape differentiation will not change for that reason, right? So now you can see with the causal picture, you can determine not only causal relations, you can also distinguish between direct and indirect causal relations, right? And finally, you have the freedom to make a desired difference. Okay, this is the first example. So in many cases, you want to go further. You want to determine all causal directions. Then if you are willing to make relatively weak assumptions on the mechanism, very oftentimes we can immediately determine causal direction, even if you have only two variables without the time information. So why? This is because of the asymmetry of the two variables under some assumptions on the causal mechanism. So right here, you can see this is a linear non-Gaussian case. We have two variables x, y. We first generate x and then generate y, okay? Where the noise E is independent from x. As you can see from here, this is a non-Gaussian case. Specifically, this is a uniform case. X is uniform and the noise is also uniform. They are independent. Y is a times x plus e right here. And then if you try to regress y on x, you can recover independent residue, right? Because you just recover the true process. But if you regress x and y, in other words, you try to look at the cause x from the perspective of y. You do linear regression, and then on the right, you can see this is the scatter plot of the residual and y, the hypothetical cause. Now you can see they are uncorrelated because whenever you do linear regression, the residual is guaranteed to be uncorrelated from the predictor. However, clearly they are dependent because the distribution of the residual is heavily sensitive to the value of y, right? They are clearly dependent. So generally, you can show that in the linear non-Gaussian case, if you don't have the right causal direction, then you cannot end up with independent residual, as you can see from here. And this is the way to discover the causal asymmetry between two variables. So even if two variable case is a fundamental case, because if you can solve the problem with two variables, then with a lot of variables, you can always try to fix some other variables or condition on some other variables, and this problem will become a two-variable problem, right? And you can determine all the direction. The same thing happens to other rather flexible causal models, including the post-nonlinear causal model right here, with the two nonlinear functions. And this nonlinear function F2 can be used to model sensor distortion, measurement distortion, and so on, and additive noise model, which is the special case of the post-nonlinear causal model. Okay, so in reality, very oftentimes the noise term is not additive. That's why the post-nonlinear model actually is very useful, especially in biology and social sciences. Okay, but in all those cases, if you have data generated by such models, you can determine, generally speaking, you can determine which one is the cause and which one is the effect. Now you can see an example. So we are given the values for the two variables, x1 and x2, right here. Okay, and we have the scatter plot. If you assume x1 causes x2, you fit the model, you estimate the residual and so on, you can see, yes, they are basically independent. But if you consider the reverse direction, assuming x2 is the cause of x1, right here, you fit the model, then you can see you can never find the independent residual. Okay, so this means that according to the post-nonlinear model, we'll favor x1 as a cause of x2. In fact, x1 is the altitude of 300 cities, and x2 is the corresponding precipitation. So clearly, x1 should be the cause. So this is a way to discover causal asymmetry, even if you have only two variables. Okay, this is the first case, first issue we want to address. You try to discover the directions for all links. Now let's consider latent variables. You already looked at this example before. In this case, we have 50 questions, and they were designed in order to really discover the underlying personality traits. What can we do? So in this case, again, we have ID data, and very oftentimes, in order to make it simpler, we can assume some parametric models, right? In some cases, we can assume it's a linear model, it's a multinomial, and clearly in this case, in this example, we have to allow a lot of latent variables because we try to uncover the hidden world that generated the answer scores. And the problem can be formulated this way. We have the measured variables, as you can see from here, and the measured variables are related to hidden variables, while hidden variables and measured variables can be related in a very flexible way. Okay, so in the general case, we allow the relations among latent variables. We allow causal influence from latent variables to the measured variables, and also relations from measured variables to the latent variables. It could be very flexible, but you can solve the problem. Specifically, here, let's look at linear case. We have some results in the nonlinear case, but at this moment, it's too complicated. Probably in one or 2 years, the results can be refined. So right here, in the linear case, first of all, this is the result by making use of the rank deficiency condition given in this paper right here. So now you can see, yes, we have all those questions, O, E questions, A questions, N questions, and C questions, right? And first of all, the results seem to be somehow consistent with the big 5 personality traits, right? You can see different kinds of questions are basically clustered right here. They are clustered, and you can see more information. For instance, some questions are actually related to multiple dimensions, like 09. I spend time reflecting on things, right? It's related to not only openness, but also neuroticism, okay? And second of all, you can see a lot of new information. Let's consider one example. In this corner, you can see from the openness questions, actually we can discover 3 latent variables, L1, L6, and L4. And if you look at the questions adjacent to those latent variables, you can see their meanings. L1 basically is about imagination, and right here, L6 is about understanding, and L4 is about creativity, right? And furthermore, you know that imagination and understanding are causes of creativity. It's sensible. And from this, we can even try to come up with new ways to do intervention. For instance, suppose I'm very good at understanding things, right? I read Wikipedia all the time. And at the same time, my imagination is not very good, and my creativity is not kind of impressive. What can we do? Maybe I should try to find a way to practice my imagination skills, right? Probably I should get away from internet and try to imagine something and try to see the consequences and so on. And this might be a way to finally improve my creativity. Okay, so once we have a very clear causal picture, we can try to find the intervention we can apply at the least price. Okay, this is the second example. Good. Now let's look at the temporal case. So we have time series, and then we can try to discover causality. A traditional way to discover causality from time series is to make use of Grandier causality, right? Grandier himself said Grandier causality is not necessarily true causality. However, under some relatively strong assumptions, Grandier causality is true causality. But here, we would like to go further. We don't try to discover causality among the measured variables, because very oftentimes causality happens in the hidden space and the relations between the hidden space and the observed variables. Let me just give one example. So suppose now we have video data and you try to see what's going on, or try to understand the video data. What can we do? So in this case, you can see we can just model video data as a high dimensional time series. And then the high dimensional time series is just an unknown flexible function of the underlying latent processes. It's a vector, right? Vector of latent processes like objects and so on. And the objects, latent processes can be related. There's only one assumption in this problem. So if you have the right latent representation or the right way to look at the world, then it takes time for causal influence to take place, meaning that the latent processes are not instantaneously related. Given the history, they are conditionally independent because there are no instantaneous relationship. That's the only essential assumption. Then given that assumption, even if everything non-parametric, generally speaking, we can recover the latent processes up to the component-wise transformation. So basically, the world is transparent because you can recover each of the latent variables, like kind of balls and so on. Let me just give one example. So this dataset is known as a mass spring dataset. Here you can see there are 5 balls moving around with different colors. Between some balls, there's a hidden spring. And from this video data as input, the system directly outputs 10 hidden variables or processes. They just correspond to the X and Y coordinates of the 5 balls. At the same time, the relations can be discovered. So now you can see everything is transparent. Just from the pixel level video data, you can immediately find a representation corresponding to the underlying meaningful objects and the relations right here, and so on. So now we are trying to develop a foundation model for video understanding so that you don't have to store pixel level video data, right? And you can directly just produce the high level concepts and relations, and later the analysis will be based on the learned representation. Okay, now let's look at multi-distribution situation very quickly. So right here we have independent but non-identically distributed data. In this case, very oftentimes we don't have to make use of parametric constraints, but still we can discover something very meaningful. First of all, you can see basically Semmelweis made use of this setting. The 2 clinics used almost the same techniques, but very different mortality rates, right? You can see the difference, the distribution was different. And then he tried to see the essential difference. And finally, he came up with a hypothesis. This is exactly what we try to do. Now let's look at example. So right here, suppose we have two data sets. Right here, this is the first one, and this is the second one, right? Or we have two domains. And suppose now we have no alignment information. We don't know the pairing information. We don't know they correspond to the same meaning. Right here, we have no idea. We just see different pictures, right? Handwritten digits. So you try to see the pairing information, and furthermore, you may want to see what's the difference between the two domains, the essential difference. Now, from your perspective, what's the difference? Right? You may say, oh, it's basically the rotation, right? The angle is different. That's great. But mathematically speaking, I can say originally this one will correspond to rotated 6, and 6 will correspond to rotated 0, and so on. This is still a valid mapping. Why? Because in this case, we are giving the marginal distributions or data corresponding to the marginal distribution, and we try to see the alignment of pairing information given by the joint distribution. We know that going from the marginal distribution to the joint distribution is so difficult. It's irreposed problem. Without proper assumptions, we cannot solve the problem. Now you can see with some assumptions, plausible assumptions, we can immediately solve the problem. What's the assumption? In order to motivate that, let's look at a more complicated problem. So right here, we have summer images and winter images. Usually we don't hide the data, right? Usually we don't stay in the same place, right, for half a year. So now you just have the two sets of images. How can you see the difference? How can you see what you mean by season? And how can you really go from one picture, say arbitrary summer image, to the counterpart in the winter? It's very difficult, right? So in order to do so, we have a generative process. Basically, images have two parts, content and style. The content basically is the information that does not change across datasets. And the style is the minimal information that can be used to explain the difference across domains. That's it. Now you can see by definition, style should be as minimal as possible. And then technically, we just make use of one assumption. We try to minimize the influence of style on image during generation or translation. How? And we can just use a minimum number of changing components or minimum number of components for style or representation. That's it. With this single condition, we can solve so many problems. Let me give one example. So this is the image generation problem. So here we are given two separate domains without the pairing information, right? And then we were asked to generate two pictures across the domains corresponding to the same content right here. So here we are given two sets of images corresponding to the female and male, and then let's just generate two pictures with the same identity or person but different genders. What can we do? In this case, we just try to identify the style variable, and we try to identify the generative process. Fortunately, under some assumptions, the generative process is identifiable under the minimal changing principle, which was just formulated. Okay, and then we can just go from the marginal distributions to the joint, and then we can just go from one data point in one domain to another domain, or we can just do data generation with multiple domains. So here at the bottom, you can see the result. On the very left, you can see the result produced by our method. Basically, you can see it's almost the same person, right? But clearly gender is different. Almost the same thing. With other SOTA methods, mainly developed by computer vision researchers, you can see very often there are some extra distortions, as you can see from here, the winkle, and here the sunglasses, right? So principles are very important, and very often we automatically formulate and make use of those principles when we try to understand the new scenarios. The issue is how we can formulate those principles so that machines can do something smartly and more powerfully. Okay, now let's look at the last part. I think the last part will maybe 8 minutes, 7 minutes will be good enough. So let's try to understand the concepts so that we can do image generation and image refinement and editing. So we know generative AI is very powerful. So with text to image models, we can just generate some pictures, nice pictures from the prompt, right? However, one thing is almost completely missing. Of course, recently, some products were just released, but basically they made use of paired data. What can we do? So basically this example. Here, first, we can ask, say, DALL-E 3 to produce a picture of a happy girl in the garden. This is very nice. Now, if you say, oh, could you make the girl angry? Now you can see, yes, the girl is angry, but the background is different, right? And everything can be very different. This is not controllable, but as a smart artist, you want to generate a very nice painting this way. You first draw a painting, and then you focus on the details you want to modify, and you can just make refinement, right? And this is our goal. We try to make sure machines can really understand concepts and relations so that it can just modify exactly what you want. So now you can see more examples. For the same reason, it's very hard for generative AI to do extrapolation. So here in this example, you can see first we generate a female face. It's very nice. Now, can you add mustache? Nothing happens. Okay. And this example, you can see you saw this example before. We want to change the facial expression, but yes, the background become very different. Okay. Later, you can see how we can deal with this problem. We start with a causal process we assumed for this problem. So with the causal process, then we can try to establish guarantees. We know, yes, all those concepts are identifiable, and then we can allow machine to directly understand the concept and relations. So this is assumed causal process to relate text and images. From text, right, we try to define meanings, and we have the atomic textual concepts and relations, right? And from images, we also have the visual concepts, the eye right here. This is text concepts. So, and clearly they are related. And furthermore, we know that generally speaking, textual concepts right here would be more informative. When we say blue, basically in text, blue is just a binary variable, right, regarding whether it's blue or not. But in the images, there are so many different levels of blue, right? So in other words, the atomic concepts derived from images would be more informative, and they are basically generated from the concepts, from the textual concepts, but with actual information. Right here, you can see it. At the same time, the relationships among the two different worlds should be as simple as possible, right? So the connections right here, the links to link textual concepts and visual concepts would be as sparse as possible to avoid the kind of actual complication. Interestingly, now you can see by making use of only two assumptions, all those concepts are identifiable from the text image pairs. So the first assumption is the sparsity constraints on the cross links right here. They should be related in a very sparse way. And second of all, we have a conditional independence in the image concepts given textual concepts. Why? Because textual concepts should provide a major information to explain the difference or the dependence in the visual concepts, although each of the visual concepts can be more informative, right? By more informative, I mean each of them can also contain the influence from some other even continuous variables, right? To describe, say, the level of blueness. Okay, now you can see on the left, you already saw this result produced by OpenAI. Now you can see the result produced by our platform. So first you generate a female image, and then you can see now, yes, although it's weird, the result is kind of natural. You just add a mustache. And this is because extrapolation is also related to the ability to go to concepts and make use of proper sparsity constraints. And on the right, you can see now you can generate a picture of a smiling girl in garden, and then you can just make the girl surprised without changing anything in the background or any other feature in the image. So it's completely controllable, just because machines can learn to focus on exactly what you want. And right here, you can see more results for image generation and refinement. So you already saw the first ones. And in this one, it's an elderly man with a cat. Now you can see we can just change the color of the shirt without changing anything else. Okay, but with other tools, including DALL-E 3, Sana, and so on, you can see some extra changes. Okay, and finally, we can just let peacock eat ice cream. So with this prompt, you can produce this picture, and then with one more prompt, a peacock eating white ice cream, you can do modification or refinement. Now you can see the only difference is to make the ice cream whiter, right? So machines can draw this picture to describe a novel scenario. At the same time, the machine can really make the change you want to enforce. Okay, so to summarize, first of all, learning causality from data, even purely observational data, is not really mysterious. Under some assumptions, we can do so. Of course, without assumption, with any assumption, we cannot go further. But fortunately, a lot of assumptions are plausible, and some assumptions, the majority of the assumptions are testable. So from data, you can try to see whether those assumptions are plausible, and if they're not, you may want to make use of another set of assumptions and corresponding methods. And second of all, you can see generative AI can clearly benefit from causal modeling. First of all, I didn't describe this part, but basically with causal modeling, you can really do counterfactual changes, right? To just make minimal change to achieve your goal. And second of all, you can see minimal change is a very important principle in order to do translation, generation, refinement, and so on. And furthermore, you can really allow machines to go to the level of concepts and relations so that the machines can generate nice pictures or nice text in new scenarios, right? It's a way to achieve extrapolation, and also it's a way to achieve kind of arbitrary changes. And finally, in the previous result, you can see DALL-E 3 made use of 600 million data pairs, while we only made use of 1.5 million data pairs. So causal principles basically provide additional constraints. As a consequence, the model or the training process would be more energy efficient thanks to the constraints or principles. And finally, we just try to make causality, causal method or causality methods transparent so that we can really make causal process behind what we see transparent in the world. Okay, thank you very much for your attention.
Thank you, Dr. Zhang, for the very informative talk. And I'll open the floor for questions now.
Thank you, everyone. Any questions?
Yeah, could you go back to the slide which right how we went from a text T to an image I with the steps in the middle?
Is it audible, Dr. Zhang?
Oh, can you repeat the question, please? It's not so clear.
Okay. So basically, could you go back for a second to the slide in which you had a text T that eventually morphed into an image I, and it had all the graphs in the middle representing the individual features of the text and then interconnected images?
You mean right here? You mean that they assume the generative process to relate images and text? Is that what you mean?
That's the one. Yeah. I just wanted to know what exactly is atomic visual concepts here. What does it represent? Is it related to in an image, say, already generated, each of the human identifiable objects within it, or is it something like pixels or something like something?
Oh, wonderful. So it's not really pixel level concept. So right here, we did a lot of studies and seemed to find the shape, different shape, color, and so on would be atomic concepts right here. So this is because if you have the generative process images right here, you don't have, if you specify the pixel level concept, then it's almost impossible to draw the connection between text and those concepts, those pixel level concepts. So I don't think, oh, okay, those results were not given. So for instance, here you can see we can learn the concept of shape. You can just try to change some of the learned atomic concepts. You can see the consequence. We did a lot of studies. Shape can be learned. For instance, here you can see we can change Hulk to Batman, the shape, and other shapes and so on. So basically the color, shape, and textual information, and so on. All those concepts can be learned. Of course, right? It may not be completely aligned with what we understand from images. And the dimensionality could be much higher. Here we use 1024 dimensions for the concepts. Is that answer? Could you go ahead?
The question here is the shape of which object is.
Yes, right here you can see. Yes, in this case you can see we can learn the shape of Batman.
But it's not in the text.
And this one may not be the atomic one. However, it's a way to combine different atomic concepts to produce these new concepts. Because if you put atomic concepts together, you have new concepts, combined concepts.
So the text is just Hulk. Batman is not in the first. So in the first image, what does it learn? Hulk?
Oh, this is the generated result. So basically, you can see this picture. Then basically, the machine can learn what you mean by Hulk, and what you mean by horse and riding and so on. And then we just do editing or refinement. We just change Hulk to Batman shape. Now you can see whenever you want, you only want to make that change, right? So if you use this prompt or use an instruction saying making the Hulk just give the Hulk the Batman shape, then you can see the picture produced in the middle right here. So this means the machine can really learn what you mean by shape and what you mean by Batman shape, and then just change the shape of the Hulk to the Batman shape.
Kept the color of the house.
So does it mean that there's to keep a relationship between the concept and the region of the image?
Yes. Yes, and we assume the relation among concepts basically are fixed. You just have different kind of concept activated.
So sorry. Basically, you have like a training data set of minimal pairs in images.
Oh, training data is. Can you say the last part again?
So does that mean that you have the training data of minimum pairs?
Yes,
no.
like.
Oh, by minimal. What do you mean by training data minimal pairs?
The minimal changes.
Yes.
So like changing.
Oh, no. Yes. Now I see the question. So basically, they are just arbitrary pairs. So in the pairs right here, you can have complex changes, right? And very often, yes, the changes could be very complex, right? You just try to cover many scenarios. The essential part is that by making use of some principles, as you can see from here, you can allow machine to just learn the basic concepts. And the basic concepts are not specified directly. You don't, like in machine learning, in computer vision, a lot of people are trying to do editing by making use of paired data. Here, we don't use paired. By making use of paired data, I mean the following thing. I have two, right here, I have the first picture, and then in the training process, I will present a picture with, say, additional mustache. I say, oh, this is basically how you can edit the image to add mustache, right? Here, you can do it with paired data. It's kind of supervised, but in our case, it's completely unsupervised. We just try to make use of the arbitrary text image pairs to understand the concepts, and then if you can discover the concepts and how the concepts can generate images, then you can just change suitable concepts, right, to make a difference, while you can just maintain the remaining concepts. So this is what we mean by minimal change. You just change exactly what you have to.
Okay, I see. Thank you very much.
Thank you.
maybe we can take one last question if somebody has any, or you're welcome to reach out to Dr. Zhang offline if you have a question.
So just for curiosity, so going from zeta t to zeta I, when you say is unsupervised, what exactly it means? Because zeta t, I understood that is your starting point, and how you can go to zeta y that you transform Hawking Batman.
Yes. So right here, now you can, when I say this unsupervised, I mean relative to the task of image editing is unsupervised because we don't have the paired data for editing, right? Alternatively, you can just have paired data, right? I can give you this picture and then give another picture with mustache. I have a label. This is supervised. In our case, we just have a bunch of paired data, right? A lot of just arbitrarily collected paired data. And just from such data, we just try to recover all those relations and concepts. Is that the answer to your question? I mean, we try to learn the concepts and align them from paired data, right? The setting is very different from, you can think of this as a pre-training process. Just from arbitrary pairs, you want to learn the inner representation with the concepts and the relations. And then later you can make use of the learned representation for a number of different tasks. One of them is to do image refinement and editing. And we are doing something similar in text generation. Is that answer to your question?
To some extent.
Or maybe you can add a few words to describe the gap.
Where I am confused is when you first say it's not supervised, but then you introduce the concept of pairs. So pairs brings me that is supervised. So where I am wrong understanding.
I see. So I have 2 points to make here. First of all, the concepts from text are also learned. We don't directly specify textual concepts. What we are given is just arbitrary prompt and image pairs or text image pairs. We just collect a lot of images with captions. That's it. We just have data pairs. And right here, if you just try to say predict the caption from the tag from the images, then we can say, oh, right here is a supervised, right? Because you try to predict this guy, one target variable from some other features. This is a supervised learning problem. But our task is different. We just make use of those features, text features and image features to learn some inner representation. And relative to the task of image generation and editing is unsupervised, because for editing, if you want to go with the supervised learning setting, you have to present paired data this way, right? Before and after editing, you have 2 images, right? And then you can just try to learn the difference. In this example, you can try to learn the difference in the image corresponding to adding mustache. And this is the supervised learning manner for image editing. We are not doing that. We just try to make use of pairs to learn the inner representation, and then we directly make use of this inner representation and prompt to generate new images or to refine images. So when I say it's unsupervised learning for image editing, I mean we are not using paired data for editing, but we make use of text and image pairs in order to derive the inner representation. Are we on the same page?
Thanks, Dr. Zhang. That answered the question. So we'll have to move forward. There are a couple of questions I still believe in the audience, but maybe they'll take it on offline.
Thank you very much.
Dr. Zhang. So we'll move on to our next paper that's Exploring LLMs for Causal Discovery in Cyber Physical Systems by Katrine Erenmule, Dr. Martha Sabal, and Conrad Debo. So, the floor is yours.
I just wanted to share first.
So, yeah, you can share your, you joined online.
Yes.
Yeah, you can just share your screen.
Just need to
Yeah.
add the settings.
Okay. Now your video.
We work this.
Sharing?
I should be sharing, right? Yes.
Yes. No, are you sharing it on Zoom? Zoom?
Yeah, so I'm not connected to your computer, so it should be.
But okay.
Yeah. Hello, and welcome to my presentation. My name is Katrin Ehrenmüller, and I'm presenting you work from our project called SENSE. We are working on cyber-physical systems, and we are looking into exploring how we can use LLMs in our use case. So cyber-physical systems in general are just smart systems with some physical parts that have more computational functionalities. In this use case, we're mostly working on smart grids as cyber-physical systems. So I first want to go into details on our use case. So here you have an example of a smart grid entity. So we have a garage with some electric vehicle chargers and a battery, and there are some sensors installed. So all the blue circles are sensors in our system. And here you can just basically measure what's happening. And then sometimes there is something happening in the system. So for example, here we have an overload at the garage that is collected by the sensor. And obviously we have some use case, stakeholders of the use case. So the facility operator in this case, so the guy operating the garage as a facility, and they want to know why did this overload happen. So ideally we get an answer that is something like there was a low battery state of charge, and that's why there was an overload, because the high charging couldn't be handled. So this is what we are working on to create as explanations in the SENSE project. And to create such explanation, we need causal knowledge in the system to answer these questions. So going into details more on the use case, we're having this, so the whole setup of this garage as the cyber-physical system setup, we have represented in a knowledge graph as part of the project. So just as a background knowledge, and we do have some causality already in the data with a very specific structure, because we need to use it for basic real-time explanations. We don't just need A causes B, but we need the type of causality. So we have it as whether A causes B or A enables B, which is sometimes just a causal relation all the time, but it does entail some different semantics. We need the temporal constraints, so whether A causes B is happening only if they happen at the same time, or if there is like some temporal lags, and then topological constraint in terms of how far A and B have to be in terms of physical proximity, basically. As an example, I have here high charging causes envelope violation. So basically, if there's a high charging at one of the chargers, this can cause an envelope violation at the garage level. So basically we have the type of causality, we have causes, then we have the overlapping as they have to be temporally overlapping. And then we have at parent platform, which means the high charge has to be within the platform where the envelope violation happens. Yes. So basically what we have in our project, we already define these causal relations with experts. So we have some ground truth data that we can work with for trying out to use LLMs to help experts in the process. So as I already kind of mentioned a bit, we have this traditional workflow of how to define causality in our cyber-physical systems. So usually you just have the setup of the system, so how everything is connected in a cyber-physical system, or in this case, a smart grid. And then we ask the expert to define some states that are interesting to them. For example, we have the overload, which is one of the states that could be interesting, and the low state of charge is another state. And we just collect basically stuff that is interesting to them. And then once we have these states, we are looking further into defining causal relations between the states. So for example, which one is the cause of the other one, to actually get to the causal model that we are interested in. So why is this not the ideal workflow? Causal discovery is super time consuming and tedious, and also just expensive because experts are expensive to talk to. So our hypothesis is basically that LLMs can offer assistance in a more hybrid workflow, as we already had in these workshops, just LLM in the loop to assist humans in the process. So there is some research already that LLMs can help as kickstarters to learning causal inference, as we already also learned in this workshop. And there has also been some investigations on LLMs for causality acquisition with promising results. So what we did is basically we are defining for our use case a hybrid workflow where we just use the setup of the system plus some trigger state that the expert tells us they're interested in. And we put this, we ask the LLM to define system states in a first step. So basically here we have two prompts. The first one is just to input the data and make sure the LLM can rephrase and like actually explain what they are doing, what they understand about the data. In the second prompt, we then ask it to actually define the system states, which is then these generated cyber-physical system states. And they should be given back to the expert basically to validate them, to say, okay, these are system states that actually make sense. Once we have these validated states, we then go back to the LLM and ask the LLM to define causal relations between these states that have been defined and validated. So in the third prompt, we then look into, so given the following state types, which causal relations do you propose in terms of these cause-effect pairs, temporal, topological, as well as causal types. Yes, so then basically we have a generated causal model that should be validated by the expert again. So then we will get, in the end, a causal model that is validated by expert, but also helped by just not having the expert to do the whole process, and maybe even finding new variations that they might not have thought about. Yes, so how did we evaluate it? We have 3 different evaluations I want to go into. So basically, the first one is just looking at the full workflow as one. So we start with the setup, plus this trigger state that's not in the picture. And then we just go through the whole process and evaluate the difference between the generated causal model and the causal model from the experts that we have from the ground truth data. So we evaluated everything with GPT-4o plus DeepSeek R1 as the state-of-the-art models. Yeah, and you can see, so we looked into precision and recall. Recall is not so great, which does make kind of sense because so we have one full workflow where we didn't really check too much on whether the generated system states and the original system states are the same. So basically, it was a bit hard to map what the models had a system state and what was proposed by the experts. But for precision, just the pairs between cause and effect were quite all right, but then going into details, the performance decreases quite a bit. So going into details on evaluation, we also just checked step 1. So basically now we just go to the generated system states and look into how they're close to the ground truth system states. So this one was a lot better. So you can see that it's just if you don't do the validation on the way, there can be some decreasing of the performance. Yeah, and then the last one is that we also just validated the last step. So we take the states from the ground truth and then just do step 2, basically. And here you can see that the recall is a lot better than before, as well as the precision being a bit better. Yeah, but also here we can see that there's a bit of a decrease going into details. Yes, so in the concluding remarks, I just want to mention that the cause-effect accuracy is quite high, with at least 67% precision, but we have decreasing performance going into details. In general, I think it's a super interesting direction to tackle this white sheet problem for experts. So not just thinking about making it like less work for the experts, but also just tackling this idea of having to start with nothing, but actually having something to, it's easier to say whether it's right or wrong than just having to come up with something. Yes, so limitations, we did not include observational data, but we already had a paper presentation that looked into that. But we also thought about including just causal falsification methods to basically have some loop to make sure this causal model is consistent with the data when we produce it. Yeah, so a very small advertisement from our side as well. We will be organizing the Centers workshop at Semantics in Vienna. So there is still paper submissions open if you want. Otherwise, I'm also happy to see some of you there if you're interested. And yeah, thank you for listening, and I'm happy to answer any questions.
Big question.
You said I have 2 questions. You said you didn't include observational data. So what did you give as an input? Was just the topology?
Yes, it was the sensors that we have and the devices that are in the system, basically, and how they are connected. And then we assumed that there is enough general knowledge from the LLMs to know how they are influencing each other.
And a very quick question, maybe I missed out. You had zero precision with the 0 recall. What did I miss?
Yeah, so this one I didn't mention, but we did check so we checked recall in terms of what was in the ground truth data, but then we did ask the expert whether they found it as a reasonable basically possible state that wasn't actually used by the expert. And then there was the precision a bit higher than the recall. Yeah.
So the recall is in interpretable standard data. But you should have, but I think you should have included those as the list of the valid ones because it doesn't, in my head, it doesn't make sense to have a 0 recall and a non-zero precision.
Yeah.
I mean, you explain it, but then it would make sense that those that you found, which are relevant, they should be included in the ground truth, and then you have a recall of, I don't know, 30%.
Yeah.
I think that was a really good example of AI in the loop.
Yeah.
As we heard from the keynote today.
True. Yeah.
So in the interest of time, we'll move forward with the next presenter. And if you have any questions, Catherine will be here and we can always talk to her. So we'll have our last. So we'll have the last paper of our workshop, Prompting or Fine-Tuning Exploring Large Language Models for Causal Graph Validation by Eunice Susanti and Nina Holzmowy.
share your screen. So hello, it's me again. So again, my name is Yuni Susanti. I'm from Fujitsu, and this time it is a joint work with Nina, which is actually a student in Osaka University. She could not be here today, but she was doing internship in our company for a while, and this is the result, of our works on this. So the title of our presentation is Prompting or Fine-Tuning. So we exploring the large language model for causal graph verification or validation. So again, in the introduction, is the conventional way to perform causal discovery is with statistical-based causal discovery, which estimate causal structures from observational data and generate a causal graph as a result. But again, this causal graph from this method is mostly unsupervised, means there is no ground truth, and normally human experts, subject matter experts, are expected to verify the result. For example, in this certain example is during the verification, we might ask whether smoking really does cause lung cancer or whether smoking really does cause yellow fingers. And again, human experts are supposed to evaluate to verify this causality, or other way is to do the controlled experiment where we, for example, assign person to smoke and then we monitor whether this person develops lung cancer, which is, of course, it is unethical, so it's not possible. So this method is, of course, have some limitation. The first is it difficult if we, as our presenter said, it is difficult and also expensive to consult to experts, and also not scalable, especially when we want to evaluate a huge, large graph and we cannot possibly check one by one. And also, sometimes it's also not feasible to do the control experiment because what I just said of like ethical concern or like when an experiment is involving human subjects. However, this information about causality actually a lot dispersed in many text sources. For example, in the research paper of the other that conducted the experiment, and they have their expert to verify the result. And these sources from the text can actually be used for verifying the causal graph from the statistical causal discovery method. So for example, here I have an excerpt from a paper which shows potential causality between osteopontin, it is a gene or protein name, and how it contributes to the progression of the prostate cancer. So we wanted to extract this kind of causal relationship between pair, and so far there is already a study on this topic, which is called causal natural language processing, because it uses NLP method to extract this relationship, and this can be used to verify the causal graph by predicting the causal relationship between each pair in the graph. So here the illustration, we have causal graph at the right, and for every pair, we use the causal NLP either from text sources like the journal or research paper, or like from knowledge base, for example, knowledge graph that is already in the form of knowledge base that also has those variables and the ground truth. So some related works on this causal relation extraction, or some say classification, can be broadly divided into two. The first is conventionally earlier method is using in a supervised setting, which is you fine-tune a large language model. For example, BERT, it's a little bit more conventional because now we have this decoder only model that and now we have this LLM-based prompting method. So, but however, it can be broadly divided into these two. It's either fine-tuning or prompting. Based on in the related works, LLM-based prompting usually performs better, especially if you use very new model. But yeah, let's see. So the research question in this presentation is, so we have those two methods, right? This prompting or fine-tuning. So we want to explore which method is actually better, at least for the specific task of causal relation extraction or classification. So again, this is our task formulation. We've given a pair of entities, or which is a variable on the node in the causal graph, for example, smoking and lung cancer. The LLM is tasked with determining with extracting the causal relationship between each of this pair. And the task is again formulated as a classification task. And here, this time we will classify each pair into whether it has causal relationship or non-causal. So it is a binary classification task which is related to our benchmark data that only has this ground truth. So the first approach is prompting. So I guess everyone should already know, but anyway, this is a little bit of definition of the prompting itself, which formally the LLM is adapted to specific task. In our case, it is a causal relation extraction task via using a natural language prompt, which is a pieces of text combined with the input and then fed to the LLM to produce an output for that specific task. And in the prompting, it can be broadly divided. We have two types here. First is the zero-shot prompt and also few-shot prompt. I will explain one by one for each prompting method. So the first is zero-shot prompting. Here, the large language model is instructed to determine the causal relationship between a pair of entities directly without being provided with any training example here. So we just ask basically. So formally here, we will have the prompt, the entity pair, the context sentences, and then we immediately ask the LLM to produce an output, which we constrain here to be causal or non-causal. This will be the example of the prompt. So for example here, is there any causal relationship between A and B in the context S? And here our sentences is the example of the context sentences. And here is the real prompt variation that we use in the experiment. We experimented with several variations. The first is we provide choices to the LLM and without using any context. So here, there is a causal relationship between A and B. There's this statement, and then we ask LLM, so whether the statement is true or false, without providing any other context or information. And then the second is we again give two choices, but this time with the context. So we provided the context sentences where the pair appears in those texts. And the last is we give three choices and also including context. Here we basically give more strict condition to the LLM that if you are not really sure, then please answer with maybe instead of binary. And then the second prompting approach is what it calls few-shot prompting, which is different to the previous zero-shot. Here we provided with few examples and specific examples that we embed directly into the prompt, and that it serves as like some kind of implicit supervision so that the LLM can learn by itself what is the task and how to answer without any parameter updates. This is also popularly called in-context learning. So yeah, the different with the previous, here we have the examples and then we give one test and then we expect the LLM to answer on this specific test example. I'll give an example here on the prompts. So here our prompt on this few shot, the blue one here is the examples. Here we only include one example on this specific for clarity. And then this red one is the test input. You can see the difference here. We don't have the result on the red one, and we expect the LLM to answer with this kind of format following the example that we already gave in the blue part. So yeah, that's the prompting method. We have two, and then the next type is fine-tuning. So LLM pre-training process itself uses a large amount of unlabeled data, so it is unsupervised. Well, the fine-tuning is basically training the model on the labeled data set and then allow the model to update the parameter for that specific task following our label example. So it requires expert annotated training data in this approach. So here, we have two choices of models that we will use on the experiment. The first is BERT model, which is to represent a smaller language model. It's roughly 250 parameters, so under 1 billion parameters. And then the second is we use GPT fine-tuning to represent larger parameters models. So first is, we will explain a bit on the BERT fine-tuning. So BERT model, I'm not sure if you are familiar, but it's trained using it's one of the early language model. So maybe not so large anymore because it has quite small parameters. And anyway, for this one, we chose a simple architecture for a fair comparison with the prompt-based method. And then the second is we fine-tune the GPT model as well. And for GPT, it has specific example. So we follow the instruction on the openai.com basically. And then we model this, we fine-tune the GPT using 2 formats. This is our experiment. We experiment using the BERT model. For the BERT, we use 3 model, BERT model, BioBERT, and PubMed BERT used for the biomedical dataset, and the normal BERT for the open domain dataset. Again, we use 2 types of dataset, the biomedical dataset and one open domain dataset. And this is our experiment result. So I will go one by one on our findings. The first is the fine-tuned model apparently outperformed the prompt-based LLM across all datasets that we in our experiment. And even with, so here in general, you can see that on the lower the fine-tuning part, it always has a higher performance. And then even with smaller model, like I said, the BERT is only like roughly 200 million parameters. It still boosts the performance. So one of the possibilities that the fine-tuning exposes the model to various ways causality can be expressed in text. That is why it leads to better performance. The finding 2 is the few-shot prompting, which is prompting but giving the LLM the examples, does not always outperform the 0-shot without any examples. We even see one significant drop here, up to 30 points. So the possible of why it happened could be that when the training examples that were provided to the LLM is very small or chosen poorly, it might confuse the model. But yeah, this needs further examination, I would say. And then our third finding is whether including the context sentences into the prompt can be effective. And yes, it is, especially in the biomedical dataset, we observe bigger performance increase. Well, in the open domain dataset, like newspaper or something, the gain can be small. And so the context and sentence helps the LLM, especially when the internal knowledge is not really enough, for example, for very domain specific, like in the biomedical. Well, in the open domain, most likely the LLM already trained on those like big data or newspaper or online content, which explains why the performance gains is much smaller. And then the last finding is we generally observe higher scores in the open domain compared to the biomedical domain for the exact same reason, because of the pre-training of the large language model itself. Here, this is the biomedical data, and this is the open domain result. And we can see that the open domain, it reached almost 96.8, the highest. Well, for the open biomedical, we only observe like roughly 77 F1 scores. So here in this paper, we present a study that explored the feasibility of applying NLP technologies, this causal relation extraction, especially LLMs, for verifying the causal graph, helping human basically. Especially we compare the prompt-based and also the fine-tuning, and in our result in this dataset, the fine-tuning models still perform better than prompt-based, even with a smaller parameters like BERT. However, the fine-tuning model, again, it needs expert annotated data, so could be expensive and difficult. So in this case, LLMs-based method like prompting also hold the promise for a causal inference. So thank you. I don't have a lot of time.
No,
so I will leave it to
one quick question.
You did not use prompting on BERT, right?
I'm sorry?
Prompting was used exclusively on GPT models, right? Okay.
Yes, we did not prompt the BERT, of course. It's only on the fine-tuning.
Okay. Just wondering if you happened to somehow manage to do that.
I don't think so, because BERT is not really generative model.
I know.
Okay.
But just in case you had done something along those lines or something like that.
I did not. I don't think it's suitable for prompting, for using BERT. It's not big enough.
I know, but just in case.
Yeah. Maybe I should try. Let's see. Okay, thank you very much.